So, what exactly is a machine learning engineer? At a high level, an ML engineer is responsible for taking machine learning models and turning them into reliable, scalable, and production-ready systems. There are 4 key responsibilities to understand: build, deploy, scale, and own. First, build. This means designing end-to-end ML systems, not just the model, but everything around it. That includes data ingestion pipelines, pre-processing steps, feature engineering, and integration with other systems. Second, deploy. A model sitting in a notebook has no business value. ML engineers package models into APIs, containers, or services so they can be used by real applications, whether that's a recommendation engine, fraud detection system, or predictive maintenance tool. Third, scale. Once a model is live, it needs to handle real-world traffic, sometimes thousands or millions of requests per second. This requires optimizing latency, ensuring uptime, and managing infrastructure efficiently. And finally, own. ML engineers are responsible for monitoring models after deployment, tracking performance, detecting data drift, and retraining models when necessary. This is why the role is often described as the bridge between data science and software engineering. Data scientists focus more on experimentation and model accuracy, while ML engineers focus on making those models work in production environments. In modern companies, especially ones building AI products, ML engineers are critical because they ensure that models actually deliver value in real-world systems. So as you go through this course, start thinking like an ML engineer. Not just, how do I build a model, but how do I build a system around this model? That mindset shift is what separates beginners from professionals. Now let's clearly understand one of the most important distinctions in the ML world: the difference between a data scientist and an ML engineer. At first glance, these roles may seem very similar. Both work with data, both build models, and both contribute to AI systems. But their goals and responsibilities are quite different. This is a case of different goals, shared mission. Let's start with data scientists. Their primary focus is on extracting insights and building accurate models. They experiment with different algorithms, tune hyperparameters, and analyze results. Their environment is often research-oriented, using tools like notebooks, Python libraries, and visualization frameworks. Their success is usually measured by metrics like accuracy, precision, recall, or model performance. On the other hand, ML engineers focus on operationalizing those models. Their job is to take a model and make it work reliably in production. That includes building data pipelines, creating APIs, handling infrastructure, and ensuring the system can scale. Instead of focusing only on accuracy, ML engineers care about latency, how fast predictions are; throughput, how many requests can be handled; reliability, system uptime and stability. Data scientists focus on experimentation and modeling, while ML engineers focus on deployment, scaling, and system performance. But here's the key point: neither role works in isolation. Successful ML systems require close collaboration between both roles. A highly accurate model is useless if it can't be deployed, and a perfectly engineered system is useless without a good model. So think of it this way. Data scientists answer, what is the best model? ML engineers answer, how do we make this model work in the real world? In this course, we're training you to think like the second. Now let's zoom out and look at the complete life cycle of a machine learning system. Every ML system, no matter how simple or complex, follows a structured process. This lifecycle includes problem definition, data, training, evaluation, and deployment. Let's walk through each stage. First is problem definition. This is where we clearly define what we're trying to solve and how success will be measured. Without a well-defined problem, even the best model won't deliver value. Next is data. This is often the most time-consuming part. Data must be collected, cleaned, and transformed into a usable format. Poor data leads to poor models, so this stage is critical. Then comes training. This is where we build and tune models using algorithms and historical data. After that is evaluation. We validate how well the model performs using metrics and ensure it generalizes well to new data. And finally, deployment. This is where the model becomes part of a real system, serving predictions to users or applications. But here's something important. This is not a one-time process. It's a loop. Once deployed, models must be monitored and updated over time. Data changes, user behavior evolves, and model performance can degrade. That's why ML engineering focuses heavily on everything after training. So instead of thinking of ML as build once and done, think of it as a continuous system that evolves over time. That mindset is essential for working in real-world AI systems. Now let's take the life cycle we just discussed and see what it looks like in a real production environment. In theory, the ML life cycle seems straightforward, but in practice, things become much more complex. Production ML systems include several critical components: data pipelines, feature engineering systems, CI/CD pipelines, and monitoring. Let's break these down. First, data pipelines. In production, data doesn't come in neatly packaged datasets. It arrives continuously, sometimes in batches, sometimes as real-time streams. ML engineers design systems to ingest, process, and store this data efficiently. Second, feature engineering. Features must be consistent between training and inference. This often requires feature stores, systems that manage and version features so models behave consistently. Third, CI/CD for ML, also known as MLOps. Just like software engineering has deployment pipelines, ML systems need automated workflows for testing, training, and deploying models. And finally, monitoring and feedback. Once a model is live, it must be continuously monitored. This includes detecting data drift, tracking performance metrics, and triggering retraining when needed. This is where ML engineering becomes truly powerful. Not just building models, but building systems that can run reliably over time. So as we move forward in this course, keep this in mind. You are not just learning ML. You are learning how to build ML systems that actually work in the real world. Now that we understand the life cycle of ML systems, let's talk about the different types of machine learning. At a high level, machine learning can be divided into three main categories: supervised learning, unsupervised learning, and reinforcement learning. On top of that, we also have deep learning, which is a powerful subset used for complex problems. Let's start with supervised learning. This is the most common type of machine learning. In supervised learning, models are trained on labeled data, meaning each input has a corresponding correct output. The goal is to learn a mapping from inputs to outputs, so the model can make accurate predictions on new data. Next is unsupervised learning. Here, the data is not labeled. The model's job is to discover patterns, structures, or relationships within the data. This is commonly used for clustering, segmentation, and anomaly detection. Then we have reinforcement learning. In this approach, models learn through interaction with an environment. They take actions, receive rewards or penalties, and gradually learn the best strategy over time. This is commonly used in robotics, gaming, and optimization problems. And finally, deep learning. Deep learning is not a separate category, but rather a subset of machine learning that uses neural networks with multiple layers. It is especially powerful for handling unstructured data like images, text, and audio. As an ML engineer, it's important to understand not just how these methods work, but when to use each one. For example, use supervised learning when you have labeled data. Use unsupervised learning when you want to discover patterns. Use deep learning when dealing with complex, high-dimensional data. In this course, we'll focus on practical applications of these techniques, especially how they fit into real-world systems on AWS. Let's now take a deeper look at supervised learning, since it is the foundation of most real-world ML applications. In supervised learning, the model learns from labeled data. This means that for every input, we already know the correct output. The model's job is to learn the relationship between the two. There are two main types of supervised learning tasks: classification and regression. Classification is used when the output is a category. For example, predicting whether an email is spam or not, or detecting whether a transaction is fraudulent. Regression, on the other hand, is used when the output is a continuous value. For example, predicting house prices, demand forecasting, or estimating delivery time. To solve these problems, we use algorithms like linear regression, logistic regression, decision trees, and more advanced methods like gradient boosting. But building a model is only part of the process. We also need to evaluate how well it performs. Common evaluation metrics include accuracy for classification problems, precision and recall for imbalanced datasets, RMSE for regression tasks. As an ML engineer, your role is not just to understand these models, but to ensure they work reliably in production. That means making sure training and inference pipelines are consistent, handling edge cases and data quality issues, ensuring predictions are delivered quickly and efficiently. Supervised learning is where most businesses start their ML journey because it directly solves measurable problems. And as we move forward, you'll see how these models are deployed and scaled using AWS services. Now let's move on to unsupervised learning. Unlike supervised learning, unsupervised learning does not rely on labeled data. Instead, the model tries to find patterns or structures within the data on its own. This makes it extremely useful when labeled data is not available, which is often the case in real-world scenarios. One of the most common techniques in unsupervised learning is clustering. Clustering algorithms group similar data points together. For example, businesses use clustering to segment customers based on behavior, preferences, or purchasing patterns. A popular algorithm for this is k-means, which divides data into clusters based on similarity. Another important technique is dimensionality reduction. In many datasets, especially large ones, there are too many features. Dimensionality reduction techniques like PCA help reduce the number of features while preserving important information. This makes models faster, more efficient, and sometimes even more accurate. Unsupervised learning is widely used for customer segmentation, anomaly detection, recommendation systems, market analysis. From an ML engineering perspective, these models often require careful interpretation. Unlike supervised learning, there is no correct answer to compare against. So evaluation becomes more about understanding patterns and business value. Also, deploying unsupervised models requires additional considerations, especially when integrating results into downstream systems. As you progress in your ML journey, you'll find that unsupervised learning plays a key role in discovering insights that aren't immediately obvious. Now let's talk about deep learning, one of the most powerful areas in modern AI. Deep learning is a subset of machine learning that uses neural networks with multiple layers to learn complex patterns in data. These models are inspired by the human brain and are capable of learning hierarchical representations, meaning each layer learns more abstract features from the previous one. Deep learning is especially effective when working with unstructured data, such as images, text, audio-video. For example, in computer vision, deep learning models can identify objects in images. In natural language processing, they can understand and generate human language. Frameworks like TensorFlow and PyTorch are commonly used to build and train these models. However, deep learning comes with its own challenges. First, it requires large amounts of data. The more complex the model, the more data it needs to learn effectively. Second, it requires significant computational power, often using GPUs or specialized hardware like TPUs. And third, it introduces additional complexity in training, tuning, and deployment. From an ML engineering perspective, deep learning systems require robust infrastructure. This includes distributed training systems, model versioning, efficient inference pipelines, hardware optimization. Deep learning powers many of the technologies we use today, from recommendation systems to generative AI. And in this course, we'll explore how these models can be built and deployed using cloud platforms like AWS. Now let's bring everything together and look at how machine learning systems are built on AWS. AWS provides a complete ecosystem for building, training, deploying, and managing ML models at scale. Let's walk through a typical ML pipeline on AWS. First, data storage. Raw data is typically stored in Amazon S3. This acts as the central data lake where all datasets are stored and accessed. Next, data processing. AWS Glue is commonly used to clean, transform, and prepare data for training. It helps automate ETL pipelines and ensures data is ready for modeling. Then comes training and deployment. Amazon SageMaker is the core service for machine learning on AWS. It allows you to build, train, and deploy models at scale. You can run experiments, tune models, and deploy them as real-time endpoints. After that, serving and orchestration. Services like AWS Lambda and step functions are used to orchestrate workflows and expose models as APIs. This allows applications to interact with ML models seamlessly. From an ML engineering perspective, AWS provides everything needed to build production-grade systems: scalable infrastructure, managed services, automation tools, integration across the entire pipeline. The key advantage is that you don't have to build everything from scratch. Instead, you can focus on designing systems and solving problems while AWS handles the underlying infrastructure. As we move forward in this course, you'll start working hands-on with these services and build your own ML pipelines. This is where theory meets real-world implementation, and where you start thinking like a true ML engineer. Now let's talk about where data actually comes from. In real-world systems, data is not coming from a single clean dataset. Instead, it comes from multiple sources, in different formats, and often at different speeds. Understanding these sources is the first step in building any ML pipeline. We can broadly categorize data into a few types. First, structured data. This includes things like databases, CSV files, and spreadsheets. This type of data is organized in rows and columns with clearly defined schemas. It's typically the easiest to work with. Next, unstructured data. This includes images, text, logs, and audio. Unlike structured data, this doesn't have a predefined format, but it often contains rich information that can be extremely valuable for machine learning. Then we have streaming data. This is real-time data that is continuously generated, such as click streams, sensor data, or financial transactions. This type of data is critical for use cases like fraud detection or recommendation systems. Finally, we have APIs and internal systems. Many ML systems rely on third-party APIs or internal services to fetch data. This could include user activity logs, transaction records, or IoT devices. One important takeaway here is that data is rarely clean or ready to use. It often requires significant pre-processing before it can be used for training. So as you design ML systems, always ask, where is this data coming from? In what format? How frequently is it updated? Answering these questions is the first step toward building a robust data pipeline. Once we understand where data comes from, the next step is ingestion, how we bring that data into our system. There are two main strategies for data ingestion: batch and streaming. Let's start with batch ingestion. Batch ingestion involves collecting data over a period of time and processing it in chunks. For example, you might run a job every night that pulls data from a database and stores it in your data lake. This approach is cost-effective and works well for historical data and offline model training. Next is streaming ingestion. Streaming is used when data needs to be processed in real time. Instead of waiting for batches, data flows continuously into the system. This is essential for use cases like fraud detection, real-time recommendations, or monitoring systems. Batch ingestion is typically scheduled, high throughput, and cost-efficient, while streaming is low latency and event-driven. There's also a hybrid approach. Some systems combine both batch and streaming, often called a lambda architecture. Batch pipelines ensure accuracy, while streaming pipelines provide real-time updates. Choosing the right approach depends on your use case. Ask yourself, do I need real-time predictions? Or can I process data in intervals? What are the cost and performance trade-offs? In modern ML systems, both approaches are often used together. As an ML engineer, your job is to design ingestion pipelines that are scalable, reliable, and aligned with business needs. Now let's talk about one of the most critical and often underestimated aspects of machine learning: data quality. Even small issues in data can have a huge impact on model performance. And the most dangerous part is that these issues often go unnoticed. Let's look at some common challenges. First, missing values. Data is rarely complete. You might have missing entries in important fields. You can choose to drop these records, fill them in, or flag them. But each decision affects your model differently. Second, duplicate records. Duplicates can skew your dataset and cause your model to learn incorrect patterns. This can lead to overfitting and poor generalization. Third, inconsistent formats. For example, dates might be stored in different formats, currencies might use different symbols, or text might have encoding issues. These inconsistencies can break pipelines and introduce errors. And finally, data drift. This happens when the distribution of your data changes over time. A model trained on old data may no longer perform well on new data. This is why data validation must be built directly into your pipeline, not treated as an afterthought. Instead of assuming data is clean, you should assume it is messy, and design systems that validate and clean it automatically. As an ML engineer, your job is to build safeguards into your pipelines. Validation checks data cleaning steps, monitoring for drift. Because in production systems, data issues are not the exception, they are the norm. Now that we understand data ingestion and quality, let's talk about where all this data is stored, the data lake. A data lake is a centralized storage system that holds all types of data in their raw format. This includes structured data, semi-structured data, and unstructured data, all stored at scale. One of the key ideas behind a data lake is ingest first, transform later. Instead of cleaning data before storing it, we store everything as is and apply transformations when needed. This is known as schema on read. Unlike traditional databases where structure is enforced up front, data lakes allow flexibility. You can apply structure later depending on your use case. This makes data lakes extremely powerful for machine learning, where different models may require different transformations. Another advantage is scalability. Data lakes are built on object storage systems, which are highly scalable and cost-effective. You can store massive amounts of data without worrying about infrastructure limits. A typical data lake workflow includes ingest raw data, apply schema when needed, scale storage efficiently. This approach allows ML systems to work with large and diverse datasets without losing flexibility. From an ML engineering perspective, the data lake is the foundation of your entire pipeline. All ingestion, transformation, feature engineering, and training processes depend on it. As we move forward, we'll see how AWS S3 acts as the backbone of data lakes and how it integrates with tools like Glue and SageMaker. Now that we understand what a data lake is, let's talk about how it's implemented in practice using Amazon S3. Amazon S3 is the backbone of most machine learning data pipelines on AWS. It's an object storage service that is highly scalable, durable, and cost-effective. Instead of storing data in traditional databases, S3 allows you to store data as objects inside buckets. This makes it ideal for handling large volumes of diverse data. In a typical ML pipeline, S3 is organized into different layers or zones. The first is the raw zone. This is where data is ingested in its original format. It could be CSV files, JSON logs, images, or any other type of data. At this stage, no transformations are applied. Everything is stored as is. Next is the processed zone. Here, data is cleaned, deduplicated, and transformed into a more usable format. This is where your ETL pipelines output their results. And finally, the feature zone. This contains model-ready features, the data that will actually be used for training and inference. These features are often versioned to ensure consistency across different models. One of the biggest advantages of S3 is its durability. It is designed to store data reliably over long periods, with extremely low risk of data loss. It also integrates seamlessly with other AWS services like Glue, Athena, and SageMaker. From an ML engineering perspective, S3 acts as the central storage layer that connects your entire pipeline. Everything flows through it. Raw data ingestion, data transformation, feature storage, model training. Understanding how to structure and organize your data in S3 is a key skill, because a well-designed data lake makes everything downstream, from ETL to modeling, much easier and more efficient. Now that data is stored in the data lake, the next step is to transform it into something useful. This is where ETL pipelines come in. ETL stands for extract, transform, and load. Let's break this down. Extract refers to pulling data from various sources, databases, APIs, logs, or streaming systems. Transform is the most important step. This is where raw data is cleaned, filtered, and converted into a usable format. For example, you might remove missing values, normalize formats, aggregate data, convert timestamps into useful features. Finally, load refers to storing the transformed data back into your data lake or into a system that can be used for training. The key idea behind ETL is automation. In real-world systems, you don't manually clean data every time. Instead, you build pipelines that run automatically, on schedules, or triggered by events. ETL pipelines ensure that your data is always clean, consistent, up to date. They also make your workflows reproducible, which is critical for debugging and maintaining ML systems. Without ETL, your models would be trained on inconsistent or unreliable data, leading to poor performance. As an ML engineer, designing efficient ETL pipelines is one of your core responsibilities. Because before you can build a great model, you need to build a great dataset. Now let's look at how ETL pipelines are implemented on AWS using a service called AWS Glue. AWS Glue is a serverless ETL service, which means you don't have to manage any infrastructure. AWS handles the provisioning and scaling of resources automatically. This allows you to focus on data transformation rather than system setup. One of the key components of Glue is the crawler. A crawler scans your data sources, such as S3, and automatically detects the schema. It then stores this metadata in the Glue data catalog. This makes your data easier to query and manage. Next, we have Glue jobs. These are scripts, typically written in PySpark or Python, that perform data transformations. You can use them to filter, join, aggregate, and clean your data. Glue jobs can be scheduled to run automatically, making your ETL pipelines fully automated. Another advantage of Glue is its integration with other AWS services. It works seamlessly with S3 for storage, Athena for querying, and SageMaker for model training. From an ML engineering perspective, Glue simplifies one of the most complex parts of the pipeline: data transformation. Instead of worrying about infrastructure, you can focus on building reliable, scalable pipelines. As you move forward, you'll likely use Glue to clean raw data, transform it into features, store it back in S3. This becomes the foundation for your machine learning workflows. Now we move into one of the most important steps in machine learning: feature engineering. Feature engineering is the process of transforming raw data into inputs that a model can actually learn from. Even the best model will fail if the features are not well designed. Let's look at some common transformations. For date fields, you might extract components like day, month, or year. For text data, you might convert it into embeddings or numerical representations. For numerical data, you might scale or normalize values so the model can learn more effectively. For categorical data, you might use techniques like one-hot encoding. The goal is to convert raw, messy data into structured, meaningful features. But there's one critical concept you must understand: consistency between training and inference. The exact same transformations applied during training must also be applied when the model is making predictions. If this consistency is broken, model performance will degrade, often silently. This is one of the most common mistakes in ML systems. That's why feature engineering is not just about transformation, it's about reproducibility. In production systems, features are often stored and versioned to ensure consistency across different models and deployments. As an ML engineer, your role is to ensure that feature pipelines are consistent, reproducible, scalable. Because feature engineering is where raw data becomes intelligence. Now, let's bring everything together and look at the complete data pipeline for a machine learning system. This is where all the pieces we've discussed come together into a unified workflow. It starts with data ingestion. Data from various sources, batch or streaming, is collected and stored in your data lake, typically in S3. Next is ETL. Using tools like Glue, the raw data is cleaned, transformed, and prepared for modeling. After that comes feature engineering. This is where the processed data is converted into model-ready features, ensuring consistency between training and inference. Then comes model training. Using services like SageMaker, Models are trained on the prepared data. Once trained, the model is deployed. It becomes part of a production system, serving predictions to applications or users. But the pipeline doesn't end there. In real-world systems, we also need monitoring and feedback. This includes tracking model performance, detecting data drift, and triggering retraining when needed. This entire process forms a continuous loop, often referred to as MLOps. From an ML engineering perspective, this pipeline is the foundation of everything. Every production ML system, regardless of industry, follows some version of this architecture. So as you move forward, don't think of ML as just building models. Think of it as designing systems, where data flows through pipelines, models learn from it, and systems continuously improve over time. That's what real-world ML engineering is all about. Now that we've covered all the individual components, let's step back and look at the complete picture, the end-to-end machine learning data pipeline. This slide brings everything together into a single flow, and this is exactly how real-world ML systems operate in production. We start with data ingestion. Data comes from multiple sources: batch systems, streaming pipelines, APIs, or internal services, and it is stored in a centralized data lake, typically in Amazon S3. This raw data is not immediately usable, so the next step is ETL: extract, transform, and load. Using tools like AWS Glue, we clean the data, remove inconsistencies, handle missing values, and transform it into a structured format. Once the data is processed, we move into feature engineering. This is where we convert cleaned data into model-ready features. These features must be consistent and reproducible, ensuring that the same transformations are applied during both training and inference. After that, we train our models. Using services like SageMaker, we build and train models on these features, tuning them to achieve the best performance. Once trained, the model is deployed into a production environment where it starts serving predictions, whether that's through APIs, applications, or automated systems. But this is not the end of the pipeline. In real-world systems, we also have monitoring and feedback loops. We track model performance, detect data drift, and identify when models need to be retrained. This continuous cycle, from data ingestion to deployment to monitoring, is what we call MLOps. It ensures that ML systems remain accurate, reliable, and up-to-date over time. The key takeaway here is this: machine learning is not just about building models. It's about building systems, where data flows through pipelines, models learn from it, and everything is continuously improved through feedback. As an ML engineer, your role is to design and maintain this entire system. And everything we've covered today, data ingestion, storage, ETL, and feature engineering, forms the foundation of that system. From here onward, we'll start building these components hands-on. Now let's define what a feature actually is. A feature is any input variable that is fed into a machine learning model. But more importantly, features are usually not raw data. They are derived or transformed from raw data to capture meaningful patterns. Let's look at a couple of examples. Suppose you have a date of birth field. Instead of feeding the raw date into the model, you would typically convert it into age. That numeric value is much more useful for prediction. Similarly, if you have transaction data, you might aggregate it to create a feature like total spend over the last 30 days. This transformation turns raw event-level data into a meaningful signal. The key idea is that features represent information in a way that models can understand. If your features are poorly designed, your model will struggle, no matter how advanced it is. That's why the quality of features directly impacts the quality of predictions. Good features capture relevant patterns, reduce noise, improve model generalization. Poor features add noise, confuse the model, lead to weak performance. As shown in your slide, features are derived inputs that capture meaningful signal, and poor features lead to weak models, regardless of algorithm sophistication. So as an ML engineer, your job is to carefully design features that reflect the underlying patterns in your data. This is where your understanding of both the data and the problem domain becomes extremely important. Because ultimately, your model can only learn from what you give it. Now that we understand what features are, the next step is understanding which features actually matter. This is where feature importance comes in. Feature importance helps us measure how much each feature contributes to the model's predictions. This is important for two main reasons: improving model performance, explaining model behavior. Let's start with performance. Not all features are equally useful. Some features carry strong signals, while others add noise. By identifying important features, we can focus on the ones that truly matter and remove the rest. This leads to simpler, faster, and more accurate models. There are several ways to measure feature importance. One common approach is tree-based importance. In models like decision trees or gradient boosting, feature importance is calculated based on how much each feature contributes to reducing error. Another approach is permutation importance. Here, we randomly shuffle the values of a feature and observe how much the model's performance drops. If performance drops significantly, that feature is important. This method is model agnostic and often more reliable. Feature importance is also critical for explainability. In many real-world applications, especially in finance or healthcare, we need to explain why a model made a certain prediction. Understanding feature importance allows us to communicate these insights to stakeholders with confidence. So as an ML engineer, feature importance is not just a technical tool, it's a bridge between models and real-world decision-making. Now that we know how to measure feature importance, the next step is deciding which features to keep. This process is called feature selection and reduction. The goal here is simple: use fewer, better features. Why is this important? Because too many features can lead to overfitting. When a model has access to too many inputs, it may start learning noise instead of real patterns. This reduces its ability to generalize to new data. Feature selection helps us eliminate unnecessary or redundant features. One common technique is correlation analysis. If two features are highly correlated, they are essentially providing the same information. In such cases, we can remove one of them without losing predictive power. Another technique is recursive feature elimination. This involves training a model, removing the least important feature, and repeating the process until we find the optimal set. The result is a leaner model that is faster to train, faster to run, easier to interpret. As your slide highlights, fewer and better features improve generalization and reduce computational overhead. From an ML engineering perspective, this also improves system efficiency, especially in production environments where latency and cost matter. So instead of trying to use every available feature, focus on selecting the right ones. Because in machine learning, more is not always better. Now let's talk about how we actually transform raw data into usable features. Feature transformation is the process of converting data into a format that models can learn from effectively. Let's look at some common types of transformations. First, scaling. Numerical features often need to be scaled so that they fall within a similar range. This helps models learn more efficiently. Two common methods are min-max normalization, standardization using z-scores. Next, encoding. Categorical data, like country or product type, cannot be directly used by most models, so we convert it into numerical form. This can be done using one-hot encoding for unordered categories, label encoding for ordered categories. Then we have log transformations. Some data distributions are highly skewed, for example, income or transaction amounts. Applying a log transform can help stabilize variance and make patterns easier for models to learn. The goal of all these transformations is to make the data more structured, more consistent, and more informative. But again, there's a critical rule. The same transformations must be applied during both training and inference. If not, your model will behave unpredictably. So feature transformation is not just about improving data, it's about ensuring consistency across your entire pipeline. And this is where ML engineering plays a key role, turning transformations into repeatable, reliable systems. Now that we've covered the basics of feature transformation, let's move into more advanced feature engineering techniques. This is where we go beyond simple transformations and start creating features that capture deeper relationships in the data. One powerful concept is feature interactions. Sometimes, individual features may not carry strong signals on their own, but when combined, they can reveal important patterns. For example, instead of just using income and age separately, you might create a ratio or interaction between them. This can help the model capture nonlinear relationships. Another important category is time-based features. For datasets with temporal data, time plays a critical role. You can create features like lag features, which capture previous values, rolling averages over time windows, seasonal indicators like day of week or month. These features are especially important in forecasting and time series models. Next, we have text and image transformations. For text data, we often convert raw text into embeddings, numerical vectors that capture semantic meaning. Techniques like TF-IDF or modern embedding models allow us to represent text in a way that models can understand. For images, we can use convolutional neural networks to extract feature vectors, compact representations that capture visual patterns. The key idea here is abstraction. We are transforming raw data into higher-level representations that make learning easier for the model. From an ML engineering perspective, advanced feature engineering requires both creativity and system design. You need to think about what transformations capture meaningful signal, how to compute them efficiently, how to reuse them across models. Because the more informative your features are, the less work your model has to do. Now let's talk about how we operationalize feature engineering using data pre-processing pipelines. So far, we've discussed transformations conceptually, but in real-world systems, these transformations must be automated, repeatable, and consistent. That's where pipelines come in. A data pre-processing pipeline is a structured sequence of steps that takes raw data and converts it into model-ready features. Typically, this includes data cleaning, feature transformation, feature generation, validation. Instead of manually applying these steps, we define them once and run them automatically. This ensures that every dataset is processed in the exact same way. Pipelines are critical for reproducibility. If you train a model today and retrain it next month, you want to ensure that the same pre-processing steps are applied. Otherwise, your results may differ unexpectedly. They also make debugging easier. If something goes wrong, you can trace it back to a specific step in the pipeline. There are several tools available for building pipelines, such as scikit-learn pipelines, TensorFlow Extended, TFX, AWS, SageMaker processing. From an ML engineering perspective, pipelines are essential because they turn feature engineering into a system. Instead of writing one-off scripts, you build reusable workflows that can scale with your data. So think of pipelines as the backbone of feature engineering in production. They ensure that everything is consistent, reproducible, scalable. and without them, it becomes very difficult to maintain reliable ML systems. Now let's discuss one of the most critical and often overlooked issues in machine learning systems: consistency between training and inference. This is sometimes referred to as training serving skew. It happens when the data transformations applied during training are different from those applied during inference. Even small differences can lead to major drops in model performance. For example, imagine you normalize a feature during training, but forget to apply the same normalization when making predictions. The model will receive inputs in a completely different scale, leading to incorrect outputs. This kind of issue is very common in production systems, and the worst part is, it often goes unnoticed until performance degrades significantly. So how do we prevent this? The key is to use shared pipelines. The same transformation logic should be used for both training and inference. This ensures that the model sees consistent data in both phases. Another important practice is feature versioning. Each model should be tied to a specific version of features, so you always know exactly what data it was trained on. This makes your system more reliable and easier to debug. From an ML engineering perspective, consistency is non-negotiable. You are not just building models, you are building systems that must behave predictably in production. So always ensure same transformations, same feature definitions, same pipeline logic, because even the best model will fail if the data it sees is inconsistent. Now let's introduce a concept that solves many of the challenges we've discussed: the feature store. A feature store is a centralized system that manages, stores, and serves features for machine learning models. Instead of recomputing features for every model, we compute them once and store them in a shared repository. This brings several advantages. First, consistency. Since all models use the same stored features, we eliminate discrepancies between training and inference. Second, reusability. Different teams and models can reuse the same features, reducing duplication of effort. Third, efficiency. Pre-computed features reduce the need for repeated computation, saving time and resources. Feature stores typically have two components: an offline store, an online store. The offline store is used for training. It contains historical data and supports batch processing. The online store is used for real-time inference. It provides low latency access to features. From an ML engineering perspective, feature stores are a game changer. They turn feature engineering into a scalable, reusable system. Instead of building features from scratch every time, you build them once and serve them everywhere. This significantly improves productivity and reliability across ML workflows. Now let's look at how feature stores are implemented on AWS using SageMaker Feature Store. SageMaker Feature Store is a fully managed service that allows you to store, manage, and serve features at scale. One of its key advantages is that it handles all the infrastructure for you. You don't need to worry about storage, indexing, or scaling. AWS manages everything behind the scenes. This allows you to focus on building features rather than managing systems. Another important feature is its integration with the SageMaker ecosystem. It works seamlessly with SageMaker pipelines, processing jobs, training workflows. This makes it easy to build end-to-end ML pipelines that are fully integrated. SageMaker Feature Store also supports both online and offline storage. This means you can use the same features for training models, serving real-time predictions. This ensures consistency across your entire pipeline. And as we discussed earlier, consistency is critical for reliable ML systems. Another key benefit is reusability. Once a feature is created and stored, it can be used across multiple models and teams. This reduces duplication and improves efficiency. From an ML engineering perspective, SageMaker Feature Store provides a production-ready solution for managing features at scale. It brings together consistency, scalability, reusability, and it plays a central role in modern MLOps workflows. As we move forward, you'll start seeing how feature stores fit into real-world ML architectures and how they simplify complex systems. Now let's bring everything together and look at the complete picture of feature engineering in a real-world machine learning system. At this point, we've covered individual concepts, feature importance, transformations, pipelines, and feature stores. But in production, these are not isolated steps. They all work together as part of a unified system. It starts with raw data. Data is collected from multiple sources, databases, logs, APIs, or streaming systems, and stored in a centralized data lake. From there, pre-processing pipelines take over. These pipelines clean the data, handle missing values, normalize formats, and generate initial features. This step ensures that the data is consistent and ready for transformation. Next comes feature engineering. This is where we apply both basic and advanced transformations, scaling, encoding, aggregations, time-based features, and interactions to convert raw data into meaningful signals. Once features are created, they are stored in a feature store. This is a critical component of modern ML systems. Instead of recomputing features every time, we store them in a centralized repository. This allows features to be reused across models and ensures consistency between training and inference. From there, models are trained using the offline feature store, which contains historical data. For real-time predictions, the model pulls features from the online store, which provides low latency access. This is where everything connects. The same features, the same transformations, and the same definitions are used across the entire pipeline. This eliminates one of the biggest risks in ML systems: inconsistencies between training and serving. And finally, we have monitoring and iteration. We continuously track feature distributions, detect drift, and update features as needed. Because feature engineering is not a one-time task, it's an ongoing process. The key takeaway here is this: feature engineering is not just about creating variables. It's about building systems that generate, store, and serve features reliably at scale. As an ML engineer, your role is to design this system end-to-end. Because ultimately, the quality of your features determines the success of your entire machine learning pipeline. Now that we understand what model training is, let's look at the complete training workflow. In real-world machine learning systems, training is not a single step. It's part of a structured pipeline. The workflow typically starts with raw data. This data is first pre-processed, cleaned, normalized, and prepared for use. Next, we apply feature engineering. This is where we transform raw data into meaningful features that the model can learn from. Once features are ready, we move into model training. Here, the model learns patterns from the training dataset. After training, we validate the model. Validation allows us to assess performance and make improvements before final evaluation. This workflow is sequential. Each stage feeds into the next. Skipping steps or rushing through them leads to unreliable models and misleading results. This workflow is critical because it ensures data consistency, reliable evaluation, reproducible results. In production systems, this workflow is often automated using pipelines. This allows models to be retrained consistently as new data becomes available. Another important point is iteration. Training is rarely done once. We continuously adjust features, tune hyperparameters, evaluate performance, and repeat the process until we achieve the desired results. So as an ML engineer, you should think of training not as a one-time task, but as a process, a pipeline that evolves over time. Because in real-world systems, this workflow is what ensures that models remain accurate, reliable, and production-ready. Now let's talk about the first and most important dataset in the training process, the training dataset. This is the portion of data that the model learns from. Typically, the training dataset makes up the largest portion of your data, often around 70 to 80%. The model uses this data to identify patterns, relationships, and trends. Every adjustment to the model's parameters is based on what it sees in the training data. Because of this, the quality of the training dataset is critical. It must represent the real-world distribution of the problem you're trying to solve. If your training data is biased, incomplete, or unrepresentative, your model will learn incorrect patterns. But there's also an important risk here: overfitting. If we rely only on the training dataset, the model may simply memorize the data instead of learning general patterns. This means it will perform very well on the training data, but poorly on new, unseen data. That's why we need additional datasets, validation, and test sets to properly evaluate performance. From an ML engineering perspective, preparing the training dataset involves ensuring data quality, maintaining representative distributions, avoiding data leakage. Because the model can only learn from what it sees, and if what it sees is flawed, everything downstream will be flawed as well. Now let's talk about the validation dataset, one of the most important tools for building reliable models. The validation dataset is a separate portion of data that is not used for training, but is used during the training process. Its purpose is to help us evaluate and improve the model while it is being developed. During training, we repeatedly check how the model performs on the validation set. This gives us feedback on how well the model is generalizing to unseen data. We use this feedback to tune hyperparameters, select the best model, compare different approaches. This is why the validation dataset acts as an iterative feedback loop. It helps us make informed decisions during the training process. Another important role of the validation set is preventing overfitting. If a model performs well on training data, but poorly on validation data, it's a clear sign that the model is overfitting. This allows us to catch problems early, before final evaluation. But there's one critical rule. The validation dataset must remain separate from the training data. We should never use validation data to directly train the model. Otherwise, we risk introducing bias into our evaluation. From an ML engineering perspective, the validation dataset is essential for building robust models. It ensures that the model is not just learning, but learning in the right way. Finally, let's talk about the test dataset, the final step in evaluating a model. The test dataset is used only once, after all training and tuning is complete. Its purpose is to provide an unbiased estimate of how the model will perform in the real world. Unlike the training and validation datasets, the test dataset must remain completely untouched during development. The model should never see this data until the very end. This ensures that the evaluation is fair and realistic. Think of the test dataset as a simulation of production. It tells us how the model is likely to perform when deployed. If a model performs well on the test dataset, we can have confidence that it will generalize to new data. Another important concept here is data leakage. If information from the test dataset leaks into training or validation, the evaluation becomes unreliable. This can lead to overly optimistic results and poor real-world performance. From an ML engineering perspective, the test dataset is essential for measuring true performance, ensuring model reliability, building stakeholder confidence. So always remember, train on training data, tune using validation data, evaluate on test data, because this separation is what ensures that your model is truly ready for production. Now, let's talk about one of the most fundamental concepts in machine learning, the bias-variance trade-off. Every model you build exists somewhere on this spectrum. Bias refers to how simple or restrictive your model is. A high-bias model makes strong assumptions about the data and may fail to capture underlying patterns. This leads to underfitting. On the other hand, variance refers to how sensitive your model is to the training data. A high-variance model learns very complex patterns, including noise, and may perform extremely well on training data, but poorly on new data. This leads to overfitting. So we have two extremes. High bias. Model is too simple. Misses patterns, performs poorly on both training and test data. High variance. Model is too complex. Memorizes noise. Performs well on training, but poorly on test data. The goal in machine learning is to find the balance, the sweet spot where both bias and variance are minimized. This is where the model generalizes well to unseen data. From an ML engineering perspective, managing this trade-off is a continuous process. We adjust model complexity, number of features, regularization techniques, training data size to move toward that optimal balance. Because ultimately, a good model is not the one that performs best on training data. It's the one that performs best on new, unseen data. Let's now make the bias variance concept more concrete by looking at underfitting and overfitting. Underfitting happens when the model is too simple to capture the underlying structure of the data. In this case, the model performs poorly on both the training dataset and the test dataset. This is a clear sign that the model has high bias. For example, imagine trying to fit a straight line to data that clearly follows a complex curve. The model simply cannot represent the true pattern. On the other hand, overfitting happens when the model is too complex. It starts to memorize the training data, including noise and random fluctuations. This leads to excellent performance on the training data, but poor performance on new data. This is a sign of high variance. Visually, you can think of underfitting as a model that is too flat or too simple. Overfitting as a model that is overly complex and wiggly. The ideal model lies in between, capturing the true pattern without memorizing noise. So how do we address these issues? To reduce underfitting, increase model complexity, add more relevant features, train longer. To reduce overfitting, use regularization, reduce model complexity, add more training data, apply techniques like dropout. As an ML engineer, recognizing these patterns early is critical, because most real-world model failures come from either underfitting or overfitting, and your goal is always to move toward that balanced, generalizable model. Now let's talk about how we measure model performance using evaluation metrics. Choosing the right metric is critical, because the metric you choose directly influences how you evaluate and improve your model. For classification problems, common metrics include accuracy, the percentage of correct predictions; precision, how many predicted positives are actually correct; recall, how many actual positives the model successfully identifies; F1 score, a balance between precision and recall. Each of these tells a different story. For example, in a medical diagnosis scenario, recall may be more important than accuracy, because missing a positive case can be critical. For regression problems, we use different metrics. Mean absolute error, or MAE, measures the average magnitude of errors. Root mean squared error, or RMSE, penalizes larger errors more heavily. So depending on your problem, the choice of metric changes. Another important consideration is imbalanced data sets. If one class dominates the data, accuracy can be misleading. For example, If 95% of your data belongs to one class, a model that always predicts that class will have 95% accuracy, but it's not useful. In such cases, metrics like F1 score or precision recall become more meaningful. From an ML engineering perspective, always ask, what does success look like for this problem? Because the right metric ensures that your model is optimized for real-world impact, not just numbers. Now let's go deeper into classification evaluation using the confusion matrix. A confusion matrix gives a detailed breakdown of how your model is performing. Instead of just telling you overall accuracy, it shows exactly where the model is making mistakes. There are 4 key components: true positives, correctly predicted positive cases; true negatives, correctly predicted negative cases; false positives, predicted positive, but actually negative false negatives; predicted negative, but actually positive. This breakdown is extremely valuable because it allows you to understand the types of errors your model is making. For example, a high number of false positives may indicate too many false alarms. A high number of false negatives may indicate missed detections. Depending on your application, one type of error may be more costly than the other. For instance, in fraud detection, false negatives mean missing fraud, very costly. False positives mean flagging legitimate transactions, inconvenient but less severe. So the confusion matrix helps you align your model with business priorities. It also forms the basis for other metrics like precision recall, F1 score. From an ML engineering perspective, the confusion matrix is one of the most powerful tools for debugging and improving classification models. Because it doesn't just tell you how well your model performs, it tells you how it fails. And understanding failure is the key to building better models. Finally, let's step beyond theory and look at how model training works in real-world production systems. In practice, training is not a one-time activity. It's part of a continuous, automated pipeline. Modern ML systems use automated workflows to handle data ingestion, feature engineering, model training, evaluation, deployment. This is often orchestrated using tools like pipelines and workflow managers. Another key component is hyperparameter tuning. Instead of manually trying different configurations, we use automated methods like grid search, random search, or more advanced techniques to find the best model settings. Model versioning is also critical. Every model you train should be tracked, including its parameters, data, and performance metrics. This allows you to compare models and roll back if needed. Then comes continuous retraining. As new data becomes available, models must be updated to stay relevant. This can be triggered by scheduled intervals, data drift, performance degradation. Finally, all of this is integrated into MLOps, the practice of applying DevOps principles to machine learning. This includes monitoring models in production, automating retraining, ensuring reliability and scalability. From an ML engineering perspective, this is where everything comes together. You're not just building models, you're building systems that continuously learn, adapt, and improve. And that's what makes machine learning truly powerful in real-world applications. Now let's look at the service that makes all of this possible: Amazon SageMaker. SageMaker is a fully managed machine learning platform provided by AWS, designed to support the entire machine learning lifecycle, from data preparation to training, deployment, and monitoring. Instead of combining multiple tools, SageMaker offers everything within a single integrated platform. SageMaker provides 3 core capabilities. First is training, which allows you to run training jobs on managed infrastructure without worrying about provisioning or maintaining compute resources. Second is deployment, where trained models can be easily deployed as API endpoints for real-time or batch predictions. Third is monitoring, which helps track model performance, detect data drift, and ensure consistent behavior in production. SageMaker also integrates seamlessly with other AWS services. Amazon S3 is used for storing data and model artifacts. AWS Identity and Access Management controls permissions and security, and AWS Glue assists with data processing and cataloging. These integrations simplify the process of building end-to-end machine learning systems. From an ML engineering perspective, SageMaker reduces complexity and operational overhead, allowing teams to move faster and build scalable solutions more efficiently. Now let's dive into the core concept of training models in SageMaker: training jobs. A training job is the fundamental unit of model training in SageMaker and represents a fully managed process that runs your training code on AWS infrastructure. You don't need to manually manage servers or environments, as everything is handled automatically. A training job consists of three main components. The first is input, which includes your training data, typically stored in S3, along with your training script and configuration such as instance type and hyperparameters. The second component is execution, where SageMaker provisions the required compute resources, runs your training script, and handles scaling if needed. It also supports distributed training across multiple instances for large-scale workloads. The third component is output. Once training is complete, the model artifacts, including trained weights and outputs, are saved back to S3. This allows for easy storage, versioning, and reuse of models. This structured process ensures consistency and reproducibility, which are critical for production systems. From an ML engineering perspective, training jobs transform model training from an isolated experiment into a scalable, trackable, and production-ready workflow. Now let's walk through the step-by-step workflow of a SageMaker training job to understand how everything comes together in practice. The process begins with uploading data to Amazon S3, which acts as the central storage layer for training datasets. Once the data is available, the next step is defining your training script. This script contains the logic for loading data, defining the model, and executing the training process. After defining the script, you configure the compute resources required for training. This includes selecting the appropriate instance type, the number of instances, and storage settings. Once everything is configured, you launch the training job. SageMaker automatically provisions the infrastructure, executes the training script, and manages the entire process without requiring manual intervention. After the training job completes, the final step is storing the model artifacts. These artifacts, such as trained model weights, are saved back to S3 for future use, deployment, or further experimentation. Each step in this workflow maps to a specific AWS service, making the system modular and easy to manage. From an ML engineering perspective, this workflow ensures reproducibility, scalability, and auditability, transforming training into a structured and reliable pipeline. Now let's explore one of the most powerful features of SageMaker: built-in algorithms. SageMaker provides a set of pre-built, optimized machine learning algorithms that can be used directly without writing custom training code. These algorithms are designed to perform efficiently at scale and are optimized for AWS infrastructure. Some commonly used built-in algorithms include XGBoost, which is highly effective for structured data and tabular prediction tasks; Linear Learner, which supports both regression and classification problems; and K-means, which is used for unsupervised clustering. These algorithms allow you to quickly build and train models without focusing on implementation details. The primary advantage of built-in algorithms is speed. They enable rapid prototyping and allow you to focus on data preparation, feature engineering, and evaluation instead of writing and debugging code. Additionally, they are optimized for distributed training, making them capable of handling large datasets efficiently. From an ML engineering perspective, built-in algorithms are particularly useful for benchmarking, standard use cases, and quickly validating ideas. However, they may not always offer the flexibility required for complex or custom use cases. In those scenarios, custom training scripts become necessary, which we will explore next. Nonetheless, built-in algorithms provide a powerful starting point for building scalable machine learning solutions on AWS. Now let's move beyond built-in algorithms and talk about custom training scripts. While built-in algorithms are great for quick experimentation, real-world machine learning often requires more flexibility. This is where custom training scripts come in. SageMaker allows you to bring your own code and use any machine learning framework you are comfortable with, such as TensorFlow, PyTorch, or scikit-learn. With custom scripts, you have full control over the training process. You can define your own model architecture, implement custom loss functions, control data loading, and design complex training loops. This is especially important for deep learning models or domain-specific applications where pre-built algorithms may not be sufficient. One of the key advantages of SageMaker is that it manages the execution environment for you. You simply provide your script, specify dependencies, and SageMaker handles the rest. This includes provisioning compute resources, running the script, and storing outputs. This approach allows you to focus on model logic rather than infrastructure. From an ML engineering perspective, custom training scripts are essential for building advanced and production-grade models. They provide the flexibility needed to adapt to different problem domains while still benefiting from SageMaker's scalability and automation. This combination of flexibility and managed infrastructure is what makes SageMaker powerful for modern ML workflows. Now let's understand how SageMaker executes your custom training code using script mode and containers. These are two approaches for defining the training environment. Script mode is the most common and recommended approach for most use cases. In this mode, you provide a Python script along with any required dependencies, and SageMaker automatically runs it inside a pre-configured container. This makes setup fast and simple, as you don't need to worry about managing the environment. Script mode is ideal when you want a balance between flexibility and simplicity. You get control over your code, while SageMaker handles the infrastructure and runtime environment. On the other hand, custom containers provide full control over the execution environment. With this approach, you create your own Docker image that includes all required libraries, dependencies, and system configurations. This is useful for advanced use cases where you need specific libraries, proprietary tools, or strict reproducibility. However, custom containers come with additional complexity. You need to build, manage, and maintain the container yourself. From an ML engineering perspective, the choice depends on your use case. Script mode is sufficient for most scenarios and allows rapid development, while custom containers are better suited for specialized or enterprise-grade requirements. Understanding when to use each approach is important, as it directly impacts development speed, reproducibility, and system complexity. Now let's talk about hyperparameter tuning, which is one of the most impactful steps in improving model performance. Hyperparameters are configuration settings that control how a model learns. Unlike model parameters, which are learned during training, hyperparameters are set before training begins. Examples of hyperparameters include learning rate, tree depth, and batch size. These values can significantly influence how well your model performs. For instance, a learning rate that is too high can cause the model to diverge, while a learning rate that is too low can make training slow and inefficient. Similarly, increasing model complexity can improve performance, but also increase the risk of overfitting. Hyperparameter tuning is the process of finding the optimal combination of these settings to achieve the best performance. Traditionally, this was done manually by trying different combinations. However, this approach is time-consuming and inefficient, especially for complex models. From an ML engineering perspective, hyperparameter tuning is where good models become great. Even small changes in hyperparameters can lead to significant improvements in accuracy and generalization. This is why tuning is considered a critical step in the model training pipeline. It ensures that your model is not only functional, but optimized for real-world performance. Now let's see how SageMaker automates hyperparameter tuning using tuning jobs. Instead of manually testing different parameter combinations, SageMaker allows you to define a range of values for each hyperparameter and automatically searches for the best configuration. This is done by launching multiple training jobs in parallel, each with different hyperparameter values. The performance of each model is evaluated based on a chosen metric, and SageMaker identifies the best performing configuration. There are different search strategies used in tuning jobs. Random search explores a wide range of parameter combinations, which is useful when you don't know which values are important. Bayesian optimization, on the other hand, uses previous results to guide the search toward more promising areas, making it more efficient. This process significantly reduces the time and effort required for tuning. Instead of manually running experiments, you can automate the entire process and focus on analyzing results. From an ML engineering perspective, tuning jobs enable scalable experimentation. They allow you to explore a large parameter space efficiently and identify optimal configurations faster. This is especially important in production systems where model performance directly impacts business outcomes. Now let's bring everything together and look at the complete end-to-end training pipeline on AWS. This is where all the concepts we've discussed come together into a unified system. The process starts with data stored in Amazon S3. This serves as the central storage for both raw data and processed datasets. Next, SageMaker training jobs are used to train the model. These jobs take the data, run the training script, and produce model artifacts. The trained model is then saved back to S3 as an artifact, typically in a packaged format that can be easily deployed. From there, the model moves into deployment and MLOps workflows. This includes registering the model, deploying it as an endpoint, monitoring its performance, and retraining it as needed. Each stage in this pipeline maps to a specific AWS service, making the system modular and easy to manage. This modular design allows teams to update, scale, and maintain each component independently. From an ML engineering perspective, this pipeline represents a production-ready workflow. It ensures that models are not just trained, but continuously improved, monitored, and integrated into real-world applications. The key takeaway is that modern machine learning is not just about building models, it's about building systems that are scalable, reliable, and continuously evolving. And AWS provides the infrastructure and tools needed to make this possible. Now let's bring everything together and look at the complete picture of training models on AWS as a real-world system. At this point, we've covered individual components such as SageMaker training jobs, built-in algorithms, custom training scripts, and hyperparameter tuning. But in production, these are not separate steps. They work together as part of a unified, end-to-end machine learning pipeline. The process begins with data. All data sets are stored in Amazon S3, which acts as the central storage layer. This ensures that data is versioned, accessible, and scalable. From there, SageMaker training jobs take over. These jobs pull data from S3, execute training scripts, and produce model artifacts. The entire process is fully managed, meaning you don't need to worry about infrastructure, scaling, or environment setup. Once training is complete, the model artifacts are saved back to S3. These artifacts represent the trained model and are ready for deployment or further evaluation. The next stage is deployment and MLOps. Models are registered, deployed as endpoints, monitored for performance, and retrained when necessary. This ensures that the model continues to perform well as data evolves over time. What's important to understand is that each stage in this pipeline maps to a specific AWS service. This makes the system modular, meaning each component can be updated or scaled independently. For example, you can update your training script without changing storage, scale compute without affecting deployment, retrain models without redesigning the pipeline. From an ML engineering perspective, this modularity is critical. It enables reproducibility, scalability, and maintainability, all of which are essential for production-grade systems. The key takeaway here is this: training models on AWS is not just about running a training job. It's about building an end-to-end system that can handle data, training, deployment, and continuous improvement. And as an ML engineer, your role is to design and manage this system, ensuring that it is reliable, efficient, and ready for real-world impact. Now that we understand what deployment is, let's talk about inference, the process of generating predictions from a deployed model. One of the most important decisions in deployment is choosing the type of inference. There are two main types of inference: real-time inference and batch inference. This decision shapes your system architecture, cost, and performance. Real-time inference is used when predictions need to be generated instantly. In this case, the model is deployed as a live endpoint, and each request triggers an immediate response. This is critical for applications where users are waiting for results, such as fraud detection or recommendation systems. Batch inference, on the other hand, is used when predictions can be generated in bulk. Instead of responding to individual requests, the model processes large datasets at once. These jobs are typically scheduled or triggered as part of a pipeline and do not require a continuously running endpoint. As your slide highlights, the choice between these two approaches is not based on model complexity, but on latency requirements and cost constraints. If your system requires immediate responses, you use real-time inference. If it can tolerate delays, batch inference is often more efficient. From an ML engineering perspective, this is a critical design decision. Choosing the wrong inference type can lead to unnecessary costs or poor user experience. So always start by asking, does the user need the prediction instantly, or can it be processed later? That answer will guide your entire deployment strategy. Let's now take a closer look at real-time inference. In this setup, the model is deployed as a persistent API endpoint that is always available to receive requests. Each time a request is sent, the model processes the input and returns a prediction almost instantly, often within milliseconds. This type of inference is designed for low-latency applications where immediate responses are required. For example, in fraud detection systems, every transaction must be evaluated in real time. Similarly, recommendation systems need to generate suggestions instantly as users interact with a platform. Chatbots and natural language processing systems also rely heavily on real-time inference to provide conversational responses. To support this, the deployment infrastructure must meet certain requirements. It needs high availability, meaning the system must be up and running almost all the time. It must also include automatic recovery mechanisms in case of failures. Additionally, the infrastructure must be optimized for low latency to ensure fast responses. As shown in your slide, real-time inference involves a continuous, always-on system that prioritizes speed and availability. From an ML engineering perspective, this comes with trade-offs. Maintaining always-on infrastructure increases cost, but it is necessary for applications where latency is critical. So real-time inference is best suited for use cases where users are actively waiting for predictions and where response time directly impacts the user experience. Now let's look at batch inference, which takes a very different approach compared to real-time systems. Instead of processing individual requests instantly, batch inference processes large volumes of data in a single job. These jobs are typically triggered on a schedule or as part of a data pipeline. For example, you might run a batch job every night to generate predictions for an entire data set. Since there is no requirement for immediate responses, the system does not need to be always running. One of the biggest advantages of batch inference is cost efficiency. Because the infrastructure is only used when needed, you avoid the cost of maintaining always-on endpoints. This makes batch processing ideal for large-scale workloads where latency is not critical. Batch inference is commonly used in scenarios like reporting and analytics, where predictions are used to generate dashboards. It is also used in demand forecasting, where models predict future trends across large datasets. Another common use case is data enrichment, where machine learning outputs are added to existing datasets for further analysis. As highlighted in your slide, batch inference is optimized for throughput rather than latency. It focuses on processing large amounts of data efficiently. From an ML engineering perspective, batch inference is a powerful tool for scaling predictions while controlling costs. It is the preferred approach when real-time responses are not required. Now let's compare real-time and batch inference to understand when to use each approach. These two paradigms represent different trade-offs in system design. Real-time inference is designed for low latency. Predictions are generated in milliseconds, making it ideal for interactive applications. However, this comes at a higher cost because the system must remain active at all times. It also requires high availability and continuous monitoring. Batch inference, on the other hand, operates with higher latency. Predictions may take minutes or even hours, depending on the size of the dataset. However, it is much more cost-efficient because resources are only used when the job runs. Availability is periodic rather than continuous. The visual in your slide clearly illustrates this trade-off. Real-time systems prioritize speed and availability, while batch systems prioritize cost and efficiency. There is also a simple design rule to follow. If a user is waiting for a response, you should use real-time inference. If the predictions are being consumed by a pipeline or used later, batch inference is usually the better choice. From an ML engineering perspective, selecting the right approach is critical. It impacts system architecture, cost, scalability, and user experience. So always align your inference strategy with your business requirements, because the success of your deployment depends on making the right trade-off between latency and cost. Now, let's move into one of the most critical aspects of deployment, endpoint configuration. When you deploy a model for real-time inference, the endpoint acts as the interface between your model and the outside world. It is essentially the contract that defines how your model will receive inputs and return predictions. Configuring an endpoint involves several important decisions. First is the instance type. This determines the compute power available for serving your model. For lightweight models, CPU instances may be sufficient, while deep learning models often require GPU-based instances to meet latency requirements. Next is the instance count. This defines how many replicas of your model are running. Having multiple instances improves availability and ensures that the system can handle concurrent requests. It also provides fault tolerance, so if one instance fails, others can continue serving traffic. Another key component is scaling policies. These define when the system should add or remove instances based on traffic patterns. Without proper scaling policies, your system may either become overloaded or unnecessarily expensive. Finally, once deployed, The endpoint is exposed as a stable HTTPS URL. Applications can send requests to this endpoint and receive predictions in real time. From an ML engineering perspective, endpoint configuration is where performance, cost, and reliability come together. A well-configured endpoint ensures low latency, high availability, and efficient resource usage. Poor configuration, on the other hand, can lead to slow responses, system failures, or excessive costs. So it's important to carefully design your endpoint based on your model requirements and expected traffic. Now let's look at how SageMaker handles model hosting. One of the biggest advantages of using SageMaker is that it provides fully managed infrastructure for deploying and serving models. This means you don't need to worry about provisioning servers, patching systems, or managing clusters. SageMaker takes care of all of that behind the scenes. When you deploy a model, SageMaker automatically sets up the infrastructure required to serve it. It also includes built-in features for reliability, such as load balancing and health checks. Load balancing ensures that incoming requests are distributed across multiple instances, while health checks monitor the status of each instance and replace any that fail. SageMaker also supports multi-model endpoints, which allow you to host multiple models on a single endpoint. This can significantly reduce costs, especially when working with a large number of models. The deployment process itself follows a clear flow. First, the trained model artifact is uploaded to S3. Then, a model object is created in SageMaker, linking the artifact with a container environment. Next, the endpoint is configured with instance types and scaling settings. Finally, the endpoint is deployed and made available for predictions. From an ML engineering perspective, SageMaker simplifies deployment by abstracting infrastructure management. This allows you to focus on model performance and system design rather than operational complexity. Now let's talk about auto-scaling, which is essential for managing real-world traffic. In production systems, traffic is rarely constant. It can vary significantly throughout the day, with periods of high demand and periods of low activity. Auto-scaling allows your system to automatically adjust resources based on this changing demand. When traffic increases, the system scales out by adding more instances to handle the load. When traffic decreases, it scales in by removing instances, reducing costs. This dynamic adjustment ensures that your system remains responsive during peak times while avoiding unnecessary expenses during low usage periods. Auto-scaling operates within defined limits. You specify the minimum and maximum number of instances, and the system adjusts within those bounds. This gives you control over both performance and cost. As illustrated in your slide, traffic patterns fluctuate over time, and auto-scaling helps match resource allocation to those patterns. From an ML engineering perspective, auto-scaling is critical for building efficient and reliable systems. Without it, you either risk system overload during peak traffic or waste resources during idle periods. So auto-scaling is not just a convenience, it's a necessity for production-grade machine learning systems. Now let's see how auto-scaling is implemented in SageMaker. SageMaker uses AWS application auto-scaling to dynamically adjust the number of instances serving your model. The process starts with defining a scaling policy. This policy determines how the system responds to changes in traffic. There are different types of policies, such as target tracking and step scaling, each designed for specific use cases. Next, you choose a metric that will trigger scaling actions. Common metrics include the number of requests per instance or CPU and GPU utilization. These metrics are monitored using AWS CloudWatch. You then define the minimum and maximum number of instances. The minimum ensures baseline availability, while the maximum controls cost by limiting how much the system can scale. Once the system is running, it continuously monitors the selected metrics and adjusts the number of instances accordingly. If traffic increases, new instances are added. If traffic decreases, instances are removed. An important concept here is the cooldown period. This is a short delay between scaling actions that prevents the system from rapidly scaling up and down in response to temporary fluctuations. From an ML engineering perspective, auto-scaling in SageMaker allows you to build systems that are both responsive and cost-efficient. It ensures that your deployment can handle real-world variability without manual intervention. Now, let's bring everything together and look at the full end-to-end deployment flow. This represents the complete life cycle of a model in production. The process starts with training. Once the model is trained, the artifact is saved to S3. Next, the model is deployed as an endpoint. This involves configuring the environment, selecting compute resources, and making the model available for real-time predictions. Once deployed, applications can send requests to the endpoint and receive predictions. This is where the model begins to deliver real-world value. However, deployment is not the final step. The system must continuously monitor performance. This includes tracking latency, detecting data drift, and evaluating model accuracy over time. If performance degrades or new data becomes available, the model must be retrained. The updated model is then redeployed, replacing or augmenting the existing system. This creates a continuous feedback loop. Train, deploy, monitor, retrain. As shown in your slide, each stage feeds into the next, forming a cycle of continuous improvement. From an ML engineering perspective, this is what defines modern machine learning systems. They are not static models, but dynamic systems that evolve over time. The key takeaway is that deployment is not the end. It is the beginning of an ongoing process that ensures your model remains accurate, relevant, and valuable in production. Now let's bring everything together and look at model deployment as a complete, real-world system. At this point, we've covered individual concepts like real-time inference, batch inference, endpoint configuration, and auto-scaling. But in production, these are not isolated components. They work together as part of a unified deployment pipeline that delivers predictions reliably and at scale. The process begins after training. Once a model is trained, it is stored as an artifact in a centralized storage system like S3. This artifact represents the learned model and is the starting point for deployment. Next, the model is deployed as an endpoint. This endpoint acts as a live API that applications can interact with. Depending on the use case, the endpoint may serve real-time predictions or be part of a batch processing pipeline. Once deployed, the system begins handling inference. Requests are sent to the endpoint, processed by the model, and predictions are returned. This is where the model starts generating real-world value. But deployment is not just about serving predictions. The system must continuously monitor performance. This includes tracking latency, system health, and model accuracy. If traffic increases, auto-scaling ensures that additional resources are provisioned to maintain performance. If traffic decreases, resources are reduced to control cost. This dynamic behavior is what makes modern ML systems efficient and scalable. Another key aspect is iteration. As new data becomes available or model performance changes, retraining is triggered. The updated model is then redeployed, replacing or improving the existing system. This creates a continuous loop. Train, deploy, monitor, and retrain. Each stage feeds into the next, ensuring that the system evolves over time and remains effective. From an ML engineering perspective, deployment is not a one-time task. It is an ongoing process that requires careful system design, monitoring, and optimization. The key takeaway is this: model deployment is about building systems, not just serving models. And your role as an ML engineer is to design systems that are reliable, scalable, and capable of continuously delivering value in real-world environments. Now let's define what an ML pipeline actually is. An ML pipeline is a structured sequence of connected steps that span the entire machine learning lifecycle. Instead of treating each step independently, pipelines link them together into a cohesive workflow. A typical pipeline includes stages such as data ingestion, pre-processing, training, evaluation, and deployment. Each stage performs a specific task and passes its output, often called an artifact, to the next stage. For example, raw data is first ingested and cleaned. The cleaned data is transformed into features. These features are used to train a model. The trained model is evaluated, and if it meets performance requirements, it is deployed. What makes pipelines powerful is that this entire process is automated and repeatable. Every time the pipeline runs, it follows the same sequence of steps using the same logic. This ensures consistency across experiments and production environments. Another key advantage is traceability. Because each step produces outputs, you can track exactly how a model was built. You know which data was used, what transformations were applied, and how the model performed. This is essential for debugging and maintaining systems. From an ML engineering perspective, pipelines bring structure to the ML lifecycle. They replace ad hoc processes with well-defined workflows that can be executed reliably. So instead of thinking of machine learning as isolated tasks, you should think of it as a pipeline, a system where each step is connected and contributes to the final outcome. Now let's break down the key components of an ML pipeline. Each component represents a stage in the machine learning lifecycle, and together they form a complete system. The first component is data processing. This involves collecting, cleaning, and validating raw data. High-quality data is essential because the performance of a model depends heavily on the quality of the data it is trained on. Next is feature engineering. In this stage, raw data is transformed into meaningful features that can be used by machine learning models. This might involve scaling values, encoding categories, or creating new variables. The third component is model training. This is where the model learns patterns from the prepared dataset. The algorithm processes the data and adjusts its parameters to improve performance. After training comes evaluation. The model is tested on validation data to measure how well it performs. Metrics such as accuracy or precision are used to determine whether the model is ready for deployment. If the model meets the required standards, it moves to deployment. In this stage, the model is made available for real-world use, typically through APIs or batch processing systems. Finally, monitoring is an ongoing component. Once deployed, the model's performance is tracked over time to detect issues such as performance degradation or data drift. From an ML engineering perspective, all these components must work together seamlessly. A failure in any one stage can affect the entire pipeline. Now let's explore why pipelines are so important in production environments. Machine learning teams that operate at scale cannot rely on manual workflows. Pipelines provide several key benefits that make them essential for production systems. The first benefit is automation. Pipelines eliminate the need for manual execution by automatically running each step. This allows systems to operate continuously without human intervention. The second benefit is reproducibility. With pipelines, the same inputs produce the same outputs every time. This consistency is critical for debugging, collaboration, and maintaining trust in the system. Another major benefit is scalability. Pipelines can handle large datasets and complex workflows efficiently. This makes them suitable for enterprise-level machine learning applications. Pipelines also reduce human error. By standardizing processes, they eliminate mistakes that often occur in manual workflows. This leads to more reliable and predictable outcomes. Finally, pipelines enable faster iteration. Because components are reusable, teams can experiment with different models or configurations quickly. This accelerates development and improves productivity. From an ML engineering perspective, these benefits are essential for building robust systems. Pipelines ensure that machine learning workflows are efficient, consistent, and scalable. The key takeaway is that pipelines are not just helpful, they are necessary for successful machine learning in production. Now let's look at SageMaker Pipelines, which is AWS's solution for building and managing machine learning workflows. SageMaker Pipelines is a fully managed service that allows you to create, automate, and monitor machine learning pipelines without managing infrastructure. This simplifies the process of building production systems. One of the biggest advantages of SageMaker Pipelines is its integration with the AWS ecosystem. It works seamlessly with other AWS services, allowing you to build complete machine learning workflows in a single environment. SageMaker Pipelines supports every stage of the ML lifecycle. You can define steps for data processing, training, evaluation, and deployment. Each step is executed in sequence, and outputs are passed between steps. Another key feature is automation. Pipelines can be triggered based on events, schedules, or data updates. This allows you to create systems that continuously improve without manual intervention. From an ML engineering perspective, SageMaker Pipelines provides the tools needed to build scalable, automated, and production-ready workflows. The key takeaway is that SageMaker Pipelines helps you move from manual experimentation to fully automated machine learning systems. Now let's understand how pipelines are structured in SageMaker. A SageMaker pipeline is made up of a series of steps, where each step performs a specific task in the machine learning workflow. These steps are connected in a sequence, and the output of one step becomes the input to the next. The most common types of steps include processing, training, and evaluation. A processing step is used for data preparation. This is where raw data is cleaned, transformed, and converted into a format suitable for training. The output of this step is typically a processed dataset. Next comes the training step. In this stage, the model is trained using the processed data. SageMaker launches a training job that uses the specified algorithm and configuration to produce a trained model. After training, the evaluation step assesses the model's performance. It generates metrics such as accuracy or loss, which are used to determine whether the model meets the required criteria. Each of these steps produces outputs, often referred to as artifacts. These artifacts flow through the pipeline, ensuring that each stage has the data it needs to operate. Pipelines in SageMaker are defined using code, typically with the SageMaker SDK. This allows you to version, reuse, and modify pipelines easily. From an ML engineering perspective, this structured approach ensures that workflows are consistent, traceable, and scalable. Instead of manually running scripts, you define a pipeline once and execute it repeatedly with confidence. Now let's introduce CI/CD for machine learning, which is a key concept in MLOps. CI/CD stands for continuous integration and continuous deployment, and it brings software engineering best practices into machine learning workflows. Continuous integration focuses on validating changes. Whenever code or pipeline definitions are updated, tests are automatically run. These tests may include checking code quality, validating data schemas, and ensuring that pipeline steps execute correctly. Continuous deployment focuses on releasing models into production. Once a model passes all evaluation criteria, it can be automatically deployed to a staging or production environment. In machine learning, CI/CD is more complex than traditional software because it involves not only code but also data and models. This means you must validate both the logic and the outputs of your system. One important concept is gating. Models are only deployed if they meet predefined performance thresholds. This ensures that only high-quality models reach production. From an ML engineering perspective, CI/CD enables automation and reliability. It reduces manual intervention, minimizes errors, and ensures that every change is tested before deployment. The key takeaway is that CI/CD transforms model deployment into a controlled, automated process rather than a manual and risky operation. Now, let's talk about model versioning and tracking, which are essential for managing machine learning systems over time. In traditional software, version control tracks changes in code. In machine learning, you must track more than just code. You also need to track data, models, and performance metrics. First, model versioning ensures that every trained model is stored with a unique identifier. This allows you to compare different models and understand how performance evolves over time. Second, data versioning tracks the datasets used for training. This is important because changes in data can significantly affect model performance. By versioning data, you can reproduce past experiments and understand differences in results. Third, performance metrics are recorded for each model version. These metrics help you evaluate which model performs best and whether it meets production requirements. Versioning also enables rollback. If a newly deployed model performs poorly, you can revert to a previous version quickly and safely. From an ML engineering perspective, versioning and tracking provide transparency and control. They ensure that every model is traceable and reproducible. The key takeaway is that versioning is not optional. It is critical for maintaining reliable and trustworthy machine learning systems. Now let's explore workflow automation, which is one of the most powerful aspects of modern ML systems. Automation eliminates the need for manual intervention and allows systems to operate continuously. There are several ways to trigger automated workflows. One common approach is data-driven triggers. When new data arrives in a data lake or storage system, the pipeline is automatically executed. This ensures that models are always trained on the latest data. Another approach is scheduled execution. Pipelines can run at fixed intervals, such as daily or weekly. This is useful for systems that require regular updates. A third approach is performance-based triggers. If a model's performance drops below a certain threshold, the system automatically initiates retraining. This helps maintain accuracy over time. Automation ensures that the entire pipeline, from data processing to deployment, runs without manual input. This reduces errors, saves time, and improves system reliability. From an ML engineering perspective, automation is what enables continuous learning systems. It ensures that models remain up to date and responsive to changing data. The key takeaway is that automation transforms machine learning from a static process into a dynamic, self-improving system. Now, let's bring everything together and look at the complete automated machine learning system. This represents the final evolution of ML pipelines. The process begins with data ingestion. New data enters the system and triggers the pipeline. The pipeline then executes each step in sequence, including data processing, feature engineering, training, and evaluation. If the model meets performance requirements, it is deployed automatically. Once deployed, the model begins serving predictions in real-world applications. However, the system does not stop there. The model is continuously monitored for performance. If issues such as data drift or accuracy degradation are detected, the pipeline is triggered again for retraining. This creates a continuous feedback loop. Data, pipeline, model, monitoring, retraining. Each stage feeds into the next, ensuring that the system evolves over time. From an ML engineering perspective, This is the ultimate goal: a fully automated system that can manage the entire lifecycle of machine learning without manual intervention. The key takeaway is that modern ML systems are not static. They are dynamic, automated, and continuously improving systems designed to adapt to real-world changes. Now, let's bring everything together and look at machine learning pipelines as a complete, fully automated system. At this point, we've covered all the key components: pipelines, SageMaker orchestration, CI/CD, versioning, and workflow automation. But in production, these are not separate ideas. They come together to form a unified system that continuously builds, deploys, and improves models. The process begins with data. New data enters the system through data ingestion pipelines, typically stored in systems like data lakes. This data becomes the trigger for the pipeline. Once triggered, the pipeline executes automatically. It starts with data processing and feature engineering, preparing the data for training. Then, the training step builds a new model using the latest data. After that, the evaluation step checks whether the model meets predefined performance thresholds. If the model performs well, it moves to deployment. The model is automatically registered, versioned, and deployed to production as an endpoint or batch system. This ensures that only validated models are exposed to real-world applications. But the system doesn't stop after deployment. Monitoring continuously tracks performance, including accuracy, latency, and data drift. If the model's performance degrades or new data patterns emerge, the system triggers retraining. This creates a continuous feedback loop: data, pipeline, training, deployment, monitoring, retraining. Each stage feeds into the next, making the system dynamic and self-improving. Another key aspect is versioning and traceability. Every model, dataset, and pipeline run is tracked. This allows you to reproduce results, audit decisions, and roll back to previous versions if needed. From an ML engineering perspective, this is the ultimate goal. You are not just building models. You are building systems that operate automatically, scale efficiently, and continuously adapt to change. The key takeaway is this: modern machine learning is not about isolated experiments. It is about designing automated, reliable, and end-to-end systems that can deliver value continuously. And as an ML engineer, your role is to architect and maintain these systems, ensuring they remain robust, scalable, and production-ready over time. Now let's talk about model drift, which is one of the core challenges in production machine learning. Model drift refers to the gradual decline in model performance over time. What makes this particularly tricky is that it happens without any changes to your code or system. The model itself hasn't changed, but the world around it has. As shown in your slide, model drift occurs because patterns shift. The relationships between inputs and outputs that the model learned during training no longer hold true in production. For example, customer behavior might change, or external conditions may evolve. One of the most important aspects of model drift is that it is a silent failure. The system does not crash. Predictions are still generated, but those predictions are increasingly wrong. This makes drift very hard to detect. Logging predictions alone is not enough. You need active monitoring systems that evaluate model performance continuously. There are different types of drift. Concept drift occurs when the relationship between features and target variables changes. Prediction drift refers to changes in the distribution of model outputs. Label drift happens when the definition of the target variable itself changes over time. All of these types require continuous evaluation. Static validation datasets are not sufficient because they do not reflect real-world changes. From an ML engineering perspective, understanding drift is critical for maintaining model reliability. The key takeaway is that models don't fail suddenly. They fail gradually, and without monitoring, you won't notice until it's too late. Now let's take a deeper look at the different types of model drift. Understanding these categories helps you diagnose issues and choose the right mitigation strategy. The first type is concept drift. This occurs when the relationship between input features and the target variable changes. In other words, the model learned a pattern that is no longer valid. For example, a model trained on past purchasing behavior may become inaccurate if customer preferences change significantly. The second type is prediction drift. This refers to changes in the distribution of model outputs. Even if you don't have access to ground truth labels, you can observe shifts in prediction patterns. For example, if your model suddenly starts predicting more positive outcomes than before, that could indicate drift. The third type is label drift. This occurs when the definition of the target variable changes over time. For instance, what was previously considered a fraudulent transaction may evolve as fraud patterns change. Each of these drift types requires different monitoring strategies. Concept drift often requires retraining, while prediction drift can be detected through output monitoring. Label drift may require updating labeling processes or business definitions. A key point highlighted in your slide is that all three types require continuous evaluation. You cannot rely on one-time validation because production environments are constantly evolving. From an ML engineering perspective, identifying the type of drift is the first step toward fixing the problem. The key takeaway is that drift is not a single issue. It is a set of different phenomena that require careful monitoring and tailored solutions. Now let's move to data drift, which is one of the most common causes of model degradation. Data drift refers to changes in the statistical distribution of input features between training and production environments. In simple terms, the data your model sees in production is different from the data it was trained on. As shown in your slide, training data is typically stable, controlled, and well understood. However, production data is often noisy, unpredictable, and constantly evolving. There are several reasons why data drift occurs. One major factor is seasonality. For example, user behavior may change during holidays or special events. Economic cycles can also influence patterns in data. Another cause is evolving user behavior. As users interact with your system over time, their preferences and actions change. This introduces new patterns that the model was not trained on. Data pipeline changes can also introduce drift. If upstream systems modify how data is collected or processed, the distribution of features may shift unexpectedly. Additionally, onboarding new user segments can introduce entirely new data patterns. The challenge with data drift is that it directly affects model performance. If the input data changes significantly, the model's predictions become less reliable. From an ML engineering perspective, detecting data drift early is crucial. It allows you to take action before performance degrades significantly. The key takeaway is that data drift is inevitable in real-world systems. The goal is not to prevent it, but to detect and manage it effectively. Now let's discuss how to detect data drift, which is a key part of any monitoring system. One of the most common techniques is statistical testing. The Kolmogorov-Smirnov test, or KS test, is widely used to compare the distribution of a feature in training data versus production data. If the distributions differ significantly, it indicates drift. Another approach is visualization. Distribution plots, such as histograms, allow you to visually compare feature distributions. By overlaying training and production data, you can quickly identify shifts. Anomaly detection is also an important technique. This involves monitoring for unusual values, such as out-of-range inputs or unexpected missing data. These anomalies can signal underlying issues in the data pipeline. As shown in your slide, combining these techniques provides a robust approach to drift detection. Statistical methods provide quantitative evidence, while visualizations offer intuitive insights. It's also important to monitor multiple features, not just a single variable. Drift in even one critical feature can impact model performance. From an ML engineering perspective, drift detection should be automated and integrated into your monitoring pipeline. This ensures continuous tracking without manual intervention. The key takeaway is that detecting drift early allows you to respond quickly, preventing performance degradation and maintaining system reliability. Now let's understand monitoring pipelines, which are the backbone of production ML observability. A monitoring pipeline runs continuously alongside your inference system, collecting signals from every stage of the machine learning workflow. As your slide illustrates, monitoring is not a single check, it is a continuous loop. It starts with ingesting live data from production systems. This includes input features, model predictions, and any available ground truth labels. Once data is collected, the pipeline tracks distributions and key metrics. This includes monitoring how input features change over time, how predictions are distributed, and how performance metrics evolve. The next step is evaluation. The system compares current metrics against baseline values or thresholds defined during training. If deviations are detected, it indicates potential issues such as drift or performance degradation. Finally, the pipeline triggers alerts. These alerts notify engineers or automated systems when something goes wrong, allowing for quick response before the issue impacts users. A key point to understand is that monitoring pipelines operate continuously, not periodically. They are designed to detect issues in near real time. From an ML engineering perspective, monitoring pipelines provide visibility into system health. Without them, you are essentially blind to how your model behaves in production. The key takeaway is that monitoring pipelines transform raw signals into actionable insights, enabling proactive maintenance of machine learning systems. Now let's discuss the key metrics that should be monitored in a production ML system. Monitoring the right metrics is critical for detecting issues early and maintaining system reliability. The first category is model performance metrics. These include accuracy, precision, recall, and F1 score. These metrics should be tracked continuously and compared against baseline values established during validation. The second category is latency. Metrics such as P50, P95, and P99 response times measure how quickly your system responds to requests. High latency can indicate infrastructure issues or increased load. Another important category is feature distribution metrics. Changes in input data distributions often signal data drift. Monitoring these distributions allows you to detect issues before they affect model performance. Error rates are also critical. This includes failed predictions, missing outputs, or unexpected behavior. A sudden increase in errors can indicate system instability. Finally, business KPIs should be monitored. These are metrics tied directly to business outcomes, such as conversion rates, revenue, or user engagement. Monitoring these ensures that your model is delivering real value. From an ML engineering perspective, combining technical metrics with business metrics provides a complete view of system health. The key takeaway is that monitoring is not just about model accuracy. It's about understanding the entire system and its impact. Now let's move to alerting and observability, which ensure that monitoring insights lead to action. Alerting involves setting thresholds for key metrics. When a metric exceeds its acceptable range, an alert is triggered. For example, If model accuracy drops below a certain threshold or latency exceeds a limit, the system generates an alert. However, designing effective alerts is not trivial. One challenge is avoiding noise. If alerts are triggered too frequently, engineers may start ignoring them. This is why techniques like rolling averages and threshold tuning are used to reduce false positives. Another important principle is proactive action. Alerts should be designed to detect issues early, before they impact users. This allows teams to respond quickly and minimize damage. Observability goes beyond alerts. It involves collecting logs, metrics, and traces to provide a complete view of system behavior. This helps engineers diagnose issues and understand root causes. Tools like monitoring dashboards and logging systems play a key role in observability. They provide real-time visibility into system performance and allow teams to investigate anomalies. From an ML engineering perspective, alerting and observability are essential for maintaining reliable systems. Monitoring without alerting is passive, while observability enables active problem-solving. The key takeaway is that monitoring is only valuable if it leads to timely and effective action. Now, let's discuss retraining strategies, which are essential for keeping models accurate over time. Since data and patterns change, models must be updated regularly to maintain performance. There are several approaches to retraining. The first is scheduled retraining. In this approach, models are retrained at fixed intervals, such as weekly or monthly. This is simple and predictable, making it easy to manage. The second approach is trigger-based retraining. Here, retraining is initiated when certain conditions are met. For example, if data drift exceeds a threshold or model performance drops below a defined level, the system automatically retrains the model. Another approach is incremental retraining. Instead of retraining from scratch, the model is updated using recent data. This is faster and more efficient, but may not always capture large changes. The final approach is full retraining. This involves rebuilding the model entirely using all available data. It is more resource-intensive, but necessary when significant drift occurs. Choosing the right strategy depends on the nature of your data. Systems with rapidly changing data require frequent or trigger-based retraining, while more stable systems can rely on scheduled updates. From an ML engineering perspective, retraining is not a one-time task. It is a continuous process embedded in the ML lifecycle. The key takeaway is that effective retraining strategies ensure that models remain relevant and accurate over time. Now let's bring everything together and look at the complete end-to-end monitoring system. The process starts with live data ingestion. Data flows into the system from production environments, including input features and model predictions. Next, the model generates predictions. These predictions are then monitored alongside input data to track changes and detect anomalies. The system continuously evaluates performance metrics and feature distributions. If drift or performance degradation is detected, it triggers alerts. Once an issue is identified, retraining pipelines are activated. The model is updated using new data and redeployed to production. This creates a continuous feedback loop. Data, prediction, monitoring, detection, retraining. As shown in your slide, this system operates continuously, providing full coverage of the ML lifecycle. It ensures that models remain accurate, reliable, and aligned with real-world conditions. From an ML engineering perspective, this is what defines a production-grade system. It is not just about deploying models, but about maintaining them over time. The key takeaway is that monitoring and retraining are not separate processes. They are tightly integrated into a continuous system that ensures long-term success. Now let's bring everything together and look at model monitoring as a complete production-grade system. At this point, we've covered key concepts like model drift, data drift, monitoring pipelines, alerting, and retraining strategies. But in real-world systems, these are not isolated components. They work together to create a continuous, self-improving machine learning system. The process begins with live data. As your model operates in production, it continuously receives new input data and generates predictions. This data is captured by the monitoring system, which tracks both input features and model outputs. Next comes monitoring. The system continuously evaluates feature distributions, prediction patterns, and performance metrics. It compares current behavior against baseline values established during training. This allows it to detect issues such as data drift, model drift, or performance degradation. When anomalies are detected, the system triggers alerts. These alerts notify engineers or automated systems that something is wrong. In advanced setups, this process can be fully automated, enabling immediate response without manual intervention. The next step is retraining. Based on predefined strategies, the system initiates retraining using fresh data. This ensures that the model adapts to new patterns and remains accurate over time. Once retrained, the updated model is redeployed into production, replacing or augmenting the previous version. This creates a continuous feedback loop: data, monitoring, detection, retraining, deployment. Each stage feeds into the next, forming a self-healing system that can adapt to real-world changes. Another important aspect is observability. Every prediction, metric, and model version is tracked. This ensures full visibility into system behavior and allows teams to diagnose issues and maintain trust in the system. From an ML engineering perspective, this is the ultimate goal. You are not just deploying models, you are building systems that monitor themselves, detect problems, and continuously improve. The key takeaway is this: production machine learning is not static. It is a dynamic, continuously evolving system designed to maintain accuracy and reliability in a changing world. Now let's talk about identity and access management, or IAM, which is the foundation of security in ML systems. IAM controls who can access resources and what actions they can perform. In a machine learning environment, this includes access to data, training jobs, models, and deployment endpoints. There are three main components of IAM. The first is users. These represent human identities, such as engineers, analysts, and auditors. Each user has specific permissions based on their role. The second component is roles. Roles are used by services and applications. For example, a training job may assume a role that allows it to read data from storage and write logs. The third component is policies. Policies define permissions in a fine-grained manner. They specify what actions are allowed or denied for a given identity. One of the most important principles in IAM is the principle of least privilege. This means granting only the minimum permissions required to perform a task. Any unnecessary permission increases the risk of misuse or security breaches. In ML systems, IAM ensures that sensitive data and models are accessed only by authorized entities. It also prevents accidental or malicious actions. From an ML engineering perspective, IAM is critical for securing workflows and maintaining control over resources. The key takeaway is that IAM is not just about access control. It is about minimizing risk and enforcing security at every level of the system. Now let's see how IAM is applied in real-world ML workflows, especially within AWS environments. In AWS, IAM roles are used extensively to secure machine learning operations. Each component of the ML pipeline is assigned a specific role with carefully scoped permissions. For example, training jobs are assigned roles that allow them to read data from storage and write logs. These roles are intentionally limited to only the permissions required for training. This prevents unnecessary access to other resources. Inference endpoints also have their own roles. These roles are even more restricted, as they typically do not require access to training data. This ensures that once a model is deployed, it cannot access sensitive datasets unnecessarily. Another important concept is the use of temporary credentials. AWS uses services like Security Token Service to provide short-lived access tokens. These tokens reduce the risk of long-term credential exposure. Service-to-service communication is also secured using IAM roles. Instead of sharing static credentials, services assume roles dynamically, ensuring secure and controlled access. From an ML engineering perspective, IAM in AWS enables fine-grained control over every stage of the ML lifecycle. The key takeaway is that secure ML systems rely on carefully designed roles and permissions, ensuring that each component has only the access it truly needs. Now let's move to data security, which is one of the most critical aspects of ML systems. Data security focuses on protecting data, both at rest and in transit. Encryption is a key mechanism used to achieve this. Encryption at rest ensures that stored data is protected. For example, data stored in systems like S3 is encrypted using managed keys. This prevents unauthorized access even if storage systems are compromised. Encryption in transit ensures that data is protected while being transferred between systems. Secure protocols such as TLS are used to prevent interception or tampering during transmission. Another important aspect is data masking and anonymization. Sensitive information such as personal identifiers is removed or transformed before being used in training pipelines. This reduces the risk of exposing sensitive data. Access control is also critical. Only authorized users and systems should be able to access datasets. This is enforced through policies and roles. From an ML engineering perspective, data security is not just about protecting data. It is about ensuring that the entire data lifecycle is secure. The key takeaway is that securing data at every stage, storage, transfer, and usage, is essential for building trustworthy ML systems. Now let's look at how data security is applied within ML pipelines. The first step is secure data ingestion. All incoming data must be validated and sanitized to ensure it is safe and properly formatted. Malformed or unauthorized data should be rejected immediately. Next is restricting access to datasets. Only the components that require raw data should have access to it. For example, training jobs may access raw datasets, while analysts work with anonymized or processed data. Logging and auditing are also essential. Every action performed on the data, including reads, writes, and deletions, should be logged. This provides visibility into how data is being used and helps detect suspicious activity. Another important aspect is preventing data leakage. This involves ensuring that sensitive data is not exposed through public access or unintended channels. Techniques such as private network configurations and restricted endpoints are used to achieve this. Additionally, secure pipeline design ensures that data flows through controlled environments. Each stage of the pipeline enforces security policies and access controls. From an ML engineering perspective, securing pipelines ensures that data remains protected throughout its life cycle. The key takeaway is that data security is not a single step. It is a continuous process embedded in every stage of the ML pipeline. Now, let's move beyond data and focus on model security, which is often overlooked but equally critical in machine learning systems. Models themselves are valuable assets. They represent intellectual property, trained knowledge, and business logic. If a model is compromised, it can lead to financial loss, competitive disadvantage, or misuse. One major risk is unauthorized access to model artifacts. These artifacts include trained weights, configurations, and metadata. If exposed, they can be copied or reused without permission. Another key risk is model theft. Attackers can gain access to stored models or replicate them by repeatedly querying inference endpoints. This is known as model extraction. Reverse engineering is also a concern. By analyzing model outputs, attackers can infer how the model behaves, potentially recreating its logic. To protect models, secure storage is essential. Model artifacts should be stored in controlled environments with strict access policies. Encryption should also be applied to ensure protection at rest. Inference endpoints must also be secured. Authentication and authorization mechanisms should be enforced to ensure that only approved users or systems can access the model. From an ML engineering perspective, model security is about protecting both the asset and its usage. The key takeaway is that models are not just outputs of the pipeline. They are critical assets that must be secured throughout their life cycle. Now let's explore the major threats that specifically target machine learning systems. Unlike traditional systems, ML models are vulnerable to unique types of attacks. The first is adversarial attacks. These involve carefully crafted inputs designed to fool the model into making incorrect predictions. Even small changes to input data can significantly impact outcomes. The second threat is data poisoning. In this case, attackers manipulate training data to introduce biases or hidden backdoors. This can degrade model performance or cause it to behave incorrectly under certain conditions. Another threat is model extraction. Attackers query the model repeatedly and use the outputs to reconstruct its behavior. Over time, they can build a replica of the model. Inference attacks are also critical. These attacks attempt to determine whether a specific data point was part of the training dataset. This can lead to privacy violations. These threats highlight the need for robust defenses, including monitoring, access control, and secure training practices. From an ML engineering perspective, understanding these threats is essential for building resilient systems. The key takeaway is that ML systems introduce new attack surfaces, and engineers must proactively design defenses to mitigate these risks. Now let's move to governance and compliance, which ensure that ML systems operate within legal and ethical boundaries. Governance defines how data and models are managed, monitored, and controlled. It establishes policies for data usage, access control, and model deployment. Compliance ensures that systems adhere to regulatory requirements. These regulations vary by industry and region, but often include strict rules around data privacy and security. For example, regulations like GDPR focus on protecting personal data and ensuring user consent. Healthcare regulations require strict handling of sensitive information. Governance also includes responsible AI practices. This involves monitoring models for bias, ensuring transparency, and maintaining human oversight where necessary. Another key component is auditability. Systems must maintain logs and records of all activities, including data access and model usage. This ensures accountability and supports regulatory audits. From an ML engineering perspective, governance and compliance are essential for building trustworthy systems that can operate at scale. The key takeaway is that governance is not just about rules. It is about ensuring that ML systems are ethical, transparent, and compliant. Now, let's discuss auditability and traceability, which are critical for maintaining accountability in ML systems. Every decision made by a model should be traceable. This means you should be able to track how the model was trained, what data was used, and how it was deployed. There are 3 key layers to track. The first is data versioning. This involves tracking datasets including their source, structure, and changes over time. This ensures that you know exactly what data was used for training. The second is model versioning. Each model should be stored with its training configuration, parameters, and performance metrics. This allows you to reproduce results and compare different versions. The third is access logging. This tracks who accessed the system, what actions they performed, and when those actions occurred. Together, these layers provide complete visibility into the ML lifecycle. Auditability is especially important for compliance. Regulators often require detailed records of how systems operate and make decisions. From an ML engineering perspective, traceability enables debugging, accountability, and continuous improvement. The key takeaway is that without auditability, ML systems cannot be trusted or maintained effectively. Now let's bring everything together and look at secure ML system design as a whole. Security in ML is not a single feature. It is an architectural principle applied across every layer of the system. At the core, data must be securely stored and managed. This includes encryption, access control, and proper data handling practices. The next layer is access and pipelines. IAM controls who can access resources, while pipelines ensure that data flows through secure and controlled environments. The outer layer includes monitoring and governance. This involves tracking system behavior, detecting anomalies, and enforcing policies. Each layer works together to create a secure and resilient system. Another important aspect is end-to-end security. Every stage of the ML lifecycle, from data ingestion to model deployment, must be secured and monitored. This ensures that vulnerabilities are minimized and risks are managed effectively. From an ML engineering perspective, secure system design is about building trust. It ensures that systems are reliable, compliant, and resistant to threats. The key takeaway is that security must be built into the system from the beginning, not added later. Now let's bring everything together and understand what a fully secure and governed machine learning system looks like in production. At this point, we've covered IAM, data security, model security, threats, governance, compliance, and auditability. But in real-world systems, these are not separate components. They work together as a unified architecture. The system begins with data. All incoming data is securely ingested, validated, and stored in encrypted environments. Access to this data is tightly controlled using IAM policies, ensuring that only authorized roles can interact with it. Next comes the pipeline. Data flows through secure pre-processing and training pipelines. Each stage enforces access controls, encryption, and logging. This ensures that data is protected throughout its life cycle and that every action is recorded. Then we move to the model. Models are trained, stored, and deployed in secure environments. Access to model artifacts is restricted, and inference endpoints are protected with authentication and authorization mechanisms. At the same time, monitoring and logging systems track everything. Every data access, model prediction, and system interaction is recorded. This provides full observability and ensures that the system remains transparent and accountable. Governance sits on top of all of this. Policies define how data is used, how models are deployed, and how systems are monitored. Compliance requirements are enforced, ensuring alignment with regulations and industry standards. If any issue arises, whether it's unauthorized access, data drift, or suspicious behavior, alerts are triggered and corrective actions can be taken immediately. This creates a secure, controlled, and auditable system from end to end. As emphasized in your material, security is not a feature that you add later. It is embedded into every layer of the architecture, from data to pipelines to models, to monitoring. From an ML engineering perspective, this is the ultimate goal. You are not just building models, you are building systems that are secure, compliant, and trustworthy. The key takeaway is this: a production ML system must be secure by design, governed by policies, and continuously monitored to ensure long-term reliability and trust. Now let's introduce distributed training, which is a core concept in scaling machine learning systems. Distributed training involves splitting the training workload across multiple machines or devices. Instead of training a model on a single machine, we distribute the computation to improve performance and enable larger models. As described in your material, distributed training works by either splitting the data or splitting the model. This allows multiple workers to process tasks simultaneously, significantly reducing training time. One of the key benefits of distributed training is parallelization. By running computations in parallel, we can train models faster and handle much larger datasets. Another important advantage is scalability. Distributed training allows us to train models that would otherwise be impossible to run on a single machine. This is especially important for modern deep learning systems. Distributed training is also the foundation of large-scale AI systems, including advanced models used in industry. However, it introduces complexity. Coordinating multiple machines, synchronizing updates, and managing communication between nodes are all challenges that must be handled carefully. From an ML engineering perspective, distributed training is a fundamental building block for scaling machine learning systems. The key takeaway is that distributed training enables both speed and scale, making it essential for modern ML architectures. Now let's explore the different types of distributed training. There are two primary approaches: data parallelism and model parallelism. In data parallelism, the same model is replicated across multiple workers. Each worker processes a different subset of the data. After computing gradients locally, the workers synchronize their updates to maintain a consistent model. In model parallelism, the model itself is divided across multiple machines. Each machine is responsible for a portion of the model. This approach is useful when the model is too large to fit into a single device. There are also hybrid approaches that combine both strategies. These are commonly used in large-scale systems to maximize efficiency. As your material highlights, each approach comes with trade-offs. Increasing parallelism can improve speed, but it also increases communication overhead and system complexity. Choosing the right strategy depends on the problem. Data parallelism is typically used for large datasets, while model parallelism is used for very large models. From an ML engineering perspective, understanding these approaches is critical for designing scalable systems. The key takeaway is that different types of distributed training offer different benefits, and selecting the right approach is essential for optimizing performance. Now let's take a deeper look at data parallelism, which is the most widely used approach in distributed training. In this method, the dataset is divided into smaller shards. Each worker processes a different shard using a copy of the same model. This allows multiple workers to compute gradients simultaneously. Once gradients are computed, they are aggregated across all workers. This ensures that the model updates are consistent and synchronized. As illustrated in your slide, the process involves several steps: sharding the dataset, computing gradients locally, aggregating gradients, and updating the model weights. There are two common approaches for gradient aggregation. The first is parameter servers, where a central server collects and distributes gradients. The second is all-reduce, where workers communicate directly to synchronize updates. Data parallelism scales well with large datasets and can significantly reduce training time. However, communication overhead can become a bottleneck as the number of workers increases. From an ML engineering perspective, managing communication efficiently is key to achieving scalability. The key takeaway is that data parallelism is the industry standard for large-scale training, providing near-linear scaling when implemented correctly. Now let's explore model parallelism, which is used when models become too large to fit into a single machine. In model parallelism, the model is divided into different parts, and each part is assigned to a separate machine or device. During training, data flows through these parts sequentially. As described in your material, this approach involves splitting model layers across devices. Each device processes its assigned portion of the model and passes intermediate outputs to the next device. One challenge with model parallelism is sequential dependency. Since each part of the model depends on the output of the previous part, computation cannot be fully parallelized. This can lead to inefficiencies. Another approach within model parallelism is tensor parallelism. This involves splitting individual weight matrices across devices, allowing for more efficient computation. This technique is commonly used in large language models. Model parallelism is essential for training extremely large models, but it introduces additional complexity, particularly in communication and coordination. From an ML engineering perspective, this approach is critical for pushing the limits of model size and capability. The key takeaway is that model parallelism enables training of very large models, but requires careful design to manage dependencies and communication overhead. Now let's move from training techniques to full large-scale machine learning systems. In production, ML systems are not just models. They are complete platforms made up of multiple interconnected components. These systems are designed to handle massive scale, high availability, and continuous operation. As highlighted in your slide, one of the core principles is horizontal scalability. This means that instead of relying on a single powerful machine, the system scales by adding more machines. This allows it to handle increasing workloads efficiently. Another key principle is high availability. Every layer of the system must be resilient to failures. If one component fails, the system should continue operating without disruption. Each layer of the system is independently scalable. For example, the data pipeline, training infrastructure, and deployment layer can scale separately based on demand. This ensures efficient resource utilization. Fault isolation is also critical. Issues in one component should not impact the entire system. This makes debugging easier and improves reliability. As shown in your architecture diagram, large-scale ML systems include multiple layers such as data pipelines, training systems, and deployment layers. From an ML engineering perspective, this represents a shift toward platform thinking. You are designing systems that must operate reliably at scale. The key takeaway is that large-scale ML systems are designed for scalability, reliability, and modularity, enabling production-grade machine learning. Now let's break down the architecture of large-scale ML systems. These systems are typically structured into multiple layers, each responsible for a specific function. The first layer is the data layer. This includes data lakes or storage systems where raw and processed data is stored. This layer must support large-scale storage and efficient retrieval. The next layer is the processing layer. This is where data is transformed and prepared using tools like distributed processing systems. Feature engineering happens at this stage. The third layer is the training layer. This includes GPU clusters or distributed training environments where models are trained at scale. Next is the serving layer. This layer handles model deployment and inference. It provides APIs or endpoints that allow applications to interact with the model. Finally, there is the monitoring layer. This layer tracks system performance, detects drift, and ensures reliability. As illustrated in your slide, these layers work together to form a complete ML system. From an ML engineering perspective, understanding how these layers interact is critical for designing scalable architectures. The key takeaway is that large-scale ML systems are composed of multiple interconnected layers, each playing a critical role in the overall system. Now let's discuss parallel processing, which is a key technique for improving performance in ML systems. Parallel processing involves executing multiple computations simultaneously. This allows systems to process large amounts of data more efficiently. There are several types of parallel processing used in ML. The first is CPU parallelism. Modern CPUs have multiple cores, allowing them to process multiple tasks at the same time. This is often used for data pre-processing and feature engineering. The second is GPU acceleration. GPUs are designed for parallel computation and can handle thousands of operations simultaneously. This makes them ideal for training deep learning models. Another important type is pipeline parallelism. In this approach, different stages of computation are overlapped. For example, while one batch is being processed, another batch is being prepared. This improves overall efficiency. Batch processing is also a form of parallelism. Large data sets are divided into smaller batches, which can be processed in parallel. From an ML engineering perspective, parallel processing is essential for scaling ML workloads. The key takeaway is that parallel processing enables faster computation and efficient resource utilization, making it a cornerstone of modern ML systems. Now let's examine the challenges that come with scaling machine learning systems. As systems grow in size and complexity, several issues arise. One major challenge is communication overhead. In distributed systems, nodes must exchange information frequently. This communication can become a bottleneck, especially during gradient synchronization. Another challenge is data consistency. In asynchronous systems, different nodes may have slightly different versions of the model. This can lead to issues such as stale gradients or race conditions. Fault tolerance is also critical. In large systems, failures are inevitable. The system must be able to recover from node failures without losing progress. Cost management is another important concern. Distributed systems, especially those using GPUs, can be expensive to run. Efficient resource utilization and scaling strategies are essential. As highlighted in your material, these challenges must be addressed to build reliable systems. From an ML engineering perspective, scaling is not just about adding more resources, it's about managing complexity. The key takeaway is that scaling ML systems introduces new challenges that require careful design and engineering. Now let's bring everything together and look at how to design a production-grade ML architecture. A production system must be built with scalability, reliability, and automation in mind. The first component is scalable data pipelines. Data must be ingested, processed, and stored efficiently. These pipelines must handle large volumes of data and operate continuously. The second component is distributed training. Models should be trained using parallel and distributed techniques to reduce training time and handle large data sets. The third component is secure and monitored deployment. Models must be deployed in a way that ensures reliability, security, and observability. Automation is another critical aspect. CI/CD pipelines should be used to automate testing, validation, and deployment. This ensures consistency and reduces manual effort. As shown in your slide, production ML is an end-to-end system. It is not a collection of isolated components, but a fully integrated architecture. Another key principle is designing for failure. Systems must be resilient and capable of handling unexpected issues. From an ML engineering perspective, this represents the final stage of maturity. The key takeaway is that production-grade ML architecture requires a holistic approach, combining scalability, automation, and reliability into a unified system. Now, let's bring everything together and reflect on what you've built throughout this course. We started with the fundamentals of machine learning engineering, understanding the life cycle, core concepts, and how ML systems are structured. From there, we moved into data engineering, feature engineering, and model training, building the foundation of any machine learning system. As we progressed, we explored how to deploy models, automate pipelines, and monitor systems in production. You learned how real-world ML systems are not static, but continuously evolving through monitoring, retraining, and optimization. We then stepped into advanced territory with MLOps, where you saw how to build systems that are reliable, scalable, and self-improving. You learned how to detect drift, monitor performance, and design feedback loops that keep models accurate over time. Security and governance added another critical layer. You now understand how to protect data, secure models, enforce access control, and ensure compliance with regulations. This is what transforms ML systems from experimental projects into enterprise-ready solutions. Finally, we explored advanced ML architectures, including distributed training, parallel processing, and large-scale system design. You now have the mindset required to design systems that operate at production scale. As emphasized in your material, production machine learning is not about isolated components. It is an end-to-end systems discipline. You are no longer just building models. You are designing systems that ingest data, train at scale, deploy reliably, monitor continuously, and improve automatically. This is the difference between a beginner and an ML engineer. The journey does not end here. The next step is to apply what you've learned. Build real systems. Work on end-to-end projects. Think in terms of architecture, scalability, and impact. The key takeaway is this: production machine learning is about designing intelligent systems that are scalable, reliable, secure, and continuously evolving in real-world environments. And now, you have the foundation to do exactly that. Now let's look at the 3 key use cases we will explore in this section. As illustrated in your slide, these include recommendation systems, fraud detection, and predictive maintenance. Each of these represents a different industry and a different type of problem, but they share common underlying patterns. The first is recommendation systems, which are used to personalize user experiences. These systems analyze user behavior and suggest relevant items, such as products or content. The second is fraud detection, which focuses on identifying suspicious activity in real time. This is widely used in banking and fintech systems. The third is predictive maintenance, which is used in industries like manufacturing and aviation to predict equipment failures before they occur. Despite their differences, these use cases follow a common pipeline. As shown in your diagram, the process starts with data. Data is collected and processed to train a model. The model then generates predictions, which lead to decisions. These decisions trigger actions, such as recommending a product, flagging a transaction, or scheduling maintenance. This flow, data, model, decision, action, is a fundamental pattern in real-world ML systems. From an ML engineering perspective, understanding these patterns helps you design systems that can be applied across domains. The key takeaway is that while use cases vary, the underlying structure of ML systems remains consistent. Now let's dive into our first use case, recommendation systems. Recommendation systems are designed to deliver personalized experiences by suggesting the most relevant items to each user. This could include products, movies, music, or any type of content. As described in your material, the core goal is personalization. Instead of showing the same content to every user, the system tailors recommendations based on individual preferences and behavior. These systems are widely used in e-commerce platforms, where they suggest products to customers. They are also used in streaming services to recommend movies, shows, or songs. The key business impact of recommendation systems is improved engagement and retention. When users see relevant content, they are more likely to interact with the platform and continue using it. Another important outcome is increased revenue. Personalized recommendations can lead to higher conversion rates and more purchases. From a technical perspective, recommendation systems rely heavily on user behavior data. This includes clicks, views, purchases, and interactions. From an ML engineering perspective, these systems must operate at scale and often require real-time inference. The key takeaway is that recommendation systems are a powerful example of how machine learning can directly influence user experience and business outcomes. Now let's explore the different types of recommendation systems. There are three main approaches: collaborative filtering, content-based filtering, and hybrid methods. Collaborative filtering is based on user behavior. It looks at patterns across users and identifies similarities. For example, if users with similar preferences liked certain items, those items can be recommended to others. Content-based filtering focuses on item attributes. It recommends items that are similar to what a user has interacted with in the past. For example, if a user watches action movies, the system will recommend other action movies. Hybrid approaches combine both methods. As highlighted in your material, most production systems use hybrid models because they provide better accuracy and handle challenges like cold starts more effectively. Each approach has its strengths and limitations. Collaborative filtering works well with large data sets, but struggles with new users. Content-based methods handle new users better, but may lack diversity. From an ML engineering perspective, choosing the right approach depends on the problem and available data. The key takeaway is that modern recommendation systems combine multiple techniques to deliver accurate and scalable personalization. Now let's look at how recommendation systems are structured in practice. As shown in your diagram, the system begins with user data. This includes interactions such as clicks, views, and purchases. This data is then used for feature engineering. Features are extracted to represent user preferences and item characteristics. Next comes model training. The model learns patterns from the data and generates recommendations. Once trained, the model is deployed to serve predictions in real time. When a user interacts with the system, recommendations are generated instantly. One of the most important aspects of recommendation systems is the feedback loop. Every user interaction, whether it is a click, skip, or purchase, is fed back into the system. This continuous feedback allows the model to improve over time and adapt to changing user preferences. From an ML engineering perspective, this requires robust pipelines, real-time processing, and continuous retraining. The key takeaway is that recommendation systems are dynamic systems that continuously learn and improve through user interactions. Now let's move to our second major use case: fraud detection. Fraud detection systems are designed to identify suspicious or fraudulent activity in real time. These systems are widely used in banking, fintech, insurance, and e-commerce platforms. As highlighted in your material, fraud detection is a highly sensitive domain. Fraudulent transactions are relatively rare, but the impact of missing them can be extremely costly. At the same time, falsely flagging legitimate transactions can negatively affect user experience. This creates a challenging problem. The system must detect fraud accurately while minimizing false positives. Another critical requirement is latency. Fraud detection systems must operate in real time, often within milliseconds. Decisions need to be made instantly to approve or block a transaction. The stakes are high. These systems must meet strict regulatory requirements and maintain trust with users. From a technical perspective, fraud detection involves analyzing transaction data, user behavior, and contextual signals. From an ML engineering perspective, this requires building systems that are fast, reliable, and scalable. The key takeaway is that fraud detection is not just a modeling problem, it is a real-time decision system with high stakes and strict performance requirements. Now let's explore the techniques used in fraud detection systems. One of the most common approaches is classification. In this method, models are trained on labeled data to distinguish between fraudulent and legitimate transactions. Algorithms like decision trees, gradient boosting, and neural networks are commonly used. Another important approach is anomaly detection. Since fraud is rare, it is often difficult to obtain labeled data. Anomaly detection models identify unusual patterns that deviate from normal behavior. Rule-based systems are also widely used. These systems apply predefined rules, such as blocking transactions above a certain amount or from unusual locations. They provide transparency and are often required for regulatory compliance. In practice, most fraud detection systems use a combination of these approaches. Feature engineering plays a critical role. Features such as transaction frequency, location changes, device information, and user behavior patterns are used to detect anomalies. From an ML engineering perspective, combining multiple techniques improves robustness and accuracy. The key takeaway is that fraud detection systems rely on a hybrid approach, combining machine learning models with rule-based logic and domain knowledge. Now let's move to our third use case, predictive maintenance. Predictive maintenance focuses on predicting equipment failures before they occur. This is widely used in industries such as manufacturing, aviation, energy, and transportation. Traditionally, maintenance was either reactive or scheduled. Reactive maintenance occurs after a failure, which can lead to downtime and costly repairs. Scheduled maintenance occurs at fixed intervals, which may result in unnecessary work. Predictive maintenance changes this approach. By using machine learning, systems can predict when a failure is likely to occur and take action proactively. As highlighted in your material, this reduces unplanned downtime and improves operational efficiency. It also helps optimize maintenance schedules and reduce costs. Another key benefit is improved safety. In industries like aviation, predicting failures can prevent accidents and save lives. From a technical perspective, predictive maintenance relies heavily on sensor data. Machines are equipped with sensors that continuously collect data such as temperature, vibration, and pressure. From an ML engineering perspective, this requires handling large volumes of time series data and building models that can detect patterns over time. The key takeaway is that predictive maintenance transforms maintenance from reactive to proactive, delivering significant operational and financial benefits. Now let's look at how predictive maintenance systems are structured. As shown in your diagram, the pipeline begins with data collection. Sensors continuously generate data from machines, including metrics like vibration, temperature, and pressure. This data is then processed using time series analysis. The goal is to identify patterns and trends over time. Next comes feature extraction. Relevant features are derived from the raw data to represent the state of the equipment. These features are then used by machine learning models to predict the likelihood of failure. The model outputs a probability or risk score. Finally, based on this prediction, maintenance actions are scheduled. For example, if the failure probability exceeds a certain threshold, a work order may be triggered. One of the most important aspects of this pipeline is real-time processing. The system must continuously monitor data and update predictions. From an ML engineering perspective, this requires robust data pipelines, scalable processing systems, and reliable deployment. The key takeaway is that predictive maintenance systems follow a structured pipeline that transforms raw sensor data into actionable maintenance decisions. Now let's step back and identify the common patterns across all these use cases. Despite differences in domains, recommendation systems, fraud detection, and predictive maintenance share several key characteristics. First, they are all data-driven systems. Decisions are based on data rather than intuition. This ensures consistency and scalability. Second, they combine real-time and batch processing. Some decisions must be made instantly, while others are based on historical data. Third, continuous monitoring is essential. Models must be tracked to ensure they remain accurate and effective over time. Another important pattern is the use of feedback loops. Outcomes from the system are fed back into the model to improve future predictions. Finally, the focus is always on business impact. Success is measured not just by model accuracy, but by real-world outcomes such as revenue, cost savings, or operational efficiency. From an ML engineering perspective, recognizing these patterns allows you to design systems that can be applied across multiple domains. The key takeaway is that while use cases differ, the underlying principles of ML system design remain consistent. Now, let's connect everything we've learned across these real-world use cases. We explored recommendation systems, fraud detection, and predictive maintenance. At first glance, these may seem like very different applications. However, they all follow a similar underlying structure. Each system begins with data. Whether it's user interactions, transaction records, or sensor readings, data is the foundation of every ML system. This data is then processed and transformed into features. These features are used to train models that can detect patterns and generate predictions. The predictions then drive decisions. In recommendation systems, the decision is what to suggest to a user. In fraud detection, it is whether to block or allow a transaction. In predictive maintenance, it is whether to schedule maintenance. Finally, these decisions lead to actions. These actions create real-world impact, improving user experience, preventing fraud, or avoiding equipment failures. Another key connection is the presence of feedback loops. Every action generates new data, which is fed back into the system to improve future predictions. From an ML engineering perspective, this unified pattern allows you to design systems that can be applied across multiple domains. The key takeaway is that while use cases differ, the core structure of ML systems remains consistent. Now let's focus on the most important shift in mindset, moving from models to business impact. In many cases, engineers focus heavily on model performance metrics, such as accuracy or precision. While these are important, they are not the ultimate goal. As emphasized in your material, success in real-world ML systems is measured by outcomes. These outcomes include revenue growth, cost savings, improved efficiency, and risk reduction. For example, in recommendation systems, the goal is not just to predict what a user might like. The goal is to increase engagement and retention. In fraud detection, the goal is not just to classify transactions. It is to minimize financial losses while maintaining a good user experience. In predictive maintenance, the goal is not just to predict failures. It is to reduce downtime and optimize operations. This shift requires thinking beyond the model. You need to understand how your system integrates into business processes and how it delivers value. From an ML engineering perspective, this means designing systems that are aligned with business goals. The key takeaway is that machine learning is not about building models. It is about creating systems that drive measurable impact. Now let's discuss what it takes to design real-world ML systems. A successful ML system is not just a model. It is an end-to-end pipeline that includes data ingestion, processing, training, deployment, and monitoring. First, you need reliable data pipelines. Data must be collected, cleaned, and transformed efficiently. Without high-quality data, even the best models will fail. Next, you need scalable training systems. Models must be trained on large datasets and updated regularly as new data becomes available. Deployment is another critical component. Models must be served reliably and efficiently, often in real time. Monitoring and feedback loops are essential. Systems must track performance, detect issues, and adapt over time. Another important aspect is integration. ML systems must work seamlessly with existing applications and workflows. From an ML engineering perspective, this requires a combination of skills, including data engineering, software engineering, and system design. The key takeaway is that building real-world ML systems requires an end-to-end approach, combining multiple components into a cohesive system. Now, let's close this section with a final takeaway. Machine learning is one of the most powerful technologies of our time, but its true value lies in how it is applied. Throughout this section, you've seen how ML systems are used to personalize experiences, prevent fraud, and optimize operations. These are not theoretical examples. They are real systems that impact millions of users every day. The most important lesson is that machine learning is not just about algorithms. It is about solving problems, creating value, and making better decisions. As an ML engineer, your role is to design systems that are not only accurate, but also scalable, reliable, and impactful. You need to think in terms of systems, not just models. You need to focus on outcomes, not just metrics. The journey from data to impact involves multiple steps: data collection, model training, decision-making, and action. Each step plays a critical role in delivering value, and most importantly, these systems must continuously improve through feedback and iteration. The key takeaway is this: machine learning in the real world is about building intelligent systems that drive meaningful impact. And now, you have the knowledge to start doing exactly that. Let's break down where the money actually goes in an ML system. As shown in your material, there are several major cost components. First, training compute is often the largest expense. Training models, especially deep learning models, requires significant CPU or GPU resources. This is typically the highest single-run cost in ML workflows. Second, data storage is another major contributor. Services like S3, data lakes, and feature stores continuously grow as your dataset increases. Storage may seem cheap initially, but at scale, it becomes a substantial cost. Third, data processing pipelines, such as ETL jobs, can also add up quickly. These pipelines often run continuously or on schedules, consuming compute resources even when not fully utilized. Another key cost area is inference endpoints. These are often deployed as always-on services. If not properly managed, idle endpoints can burn money without delivering value. Finally, monitoring and logging infrastructure adds additional overhead. At high scale, collecting metrics, logs, and traces can become surprisingly expensive. The diagram in your material clearly shows that cost is distributed across the entire ML lifecycle, not just training. From an ML engineering perspective, this means optimization cannot focus on just one stage. You need to think holistically about the system. The key takeaway is that cost exists everywhere, from data to deployment, and understanding these components is the first step toward optimization. Now let's explore the core strategies for optimizing cost. As outlined in your material, the first strategy is right-sizing resources. This means selecting the appropriate instance type and size based on actual workload requirements. Over-provisioning is one of the most common and avoidable sources of waste. The second strategy is intelligent autoscaling. Instead of running resources continuously, systems should scale up when demand increases and scale down aggressively when demand drops. Third, optimizing data pipelines is critical. Redundant transformations, inefficient queries, and unnecessary data movement all increase compute costs. Streamlining these pipelines can significantly reduce expenses. Another key strategy is continuous monitoring. As emphasized in your material, tracking utilization and spending in real time allows you to detect inefficiencies early before they become costly problems. An important mindset here is that optimization is not a one-time task. It is an ongoing process. From an ML engineering perspective, these strategies must be built into the system design itself, not added later. The key takeaway is that cost optimization requires a combination of smart resource management, automation, and continuous visibility into system performance. Now let's focus specifically on training efficiency, which is one of the biggest opportunities for cost savings. As highlighted in your material, every unnecessary training epoch burns GPU budget. This is a critical insight. Training longer than needed directly translates into higher costs. One effective strategy is early stopping. By monitoring validation performance, you can stop training when the model stops improving, avoiding unnecessary compute usage. Another powerful technique is using curated datasets. Instead of training on large raw datasets, you can use smaller, high-quality datasets that still capture the essential patterns. Model optimization techniques such as pruning and quantization can also reduce model size and training time. One of the most impactful strategies mentioned in your material is leveraging pre-trained models. Instead of training from scratch, you can fine-tune an existing model. This can reduce training costs by up to 10 to 100 times. Distributed training is another approach, but it must be used carefully. While it speeds up training, it can also increase costs if not managed efficiently. From an ML engineering perspective, the goal is to train smarter, not longer. The key takeaway is that optimizing training workflows can lead to massive cost savings without sacrificing model performance. Now, let's talk about one of the most important decisions in cost optimization: instance selection. As your material highlights, instance selection directly determines cost efficiency. Choosing the wrong instance type is one of the most common and preventable mistakes. There are three main categories of compute resources: CPUs, GPUs, and specialized accelerators. CPUs are best suited for tasks like data pre-processing, feature engineering, and lightweight inference. They are relatively low cost and widely available. GPUs, on the other hand, are optimized for deep learning workloads. They provide high performance for training and large-scale inference, but they are significantly more expensive. Specialized accelerators, such as TPUs or AWS-specific hardware, offer even higher performance for certain workloads. These can provide better performance per dollar at scale, but require specific configurations. The key challenge is balancing cost and performance. Using a GPU for a task that can run on a CPU is wasteful. On the other hand, using a CPU for a deep learning workload may lead to inefficient training times. Another common issue is over-provisioning, allocating more resources than necessary. From an ML engineering perspective, instance selection should always be driven by workload requirements and utilization metrics. The key takeaway is that choosing the right infrastructure is one of the most powerful ways to control costs while maintaining performance. Now let's take a deeper look at compute options and how they impact cost. As highlighted in your material, Choosing between CPU, GPU, and specialized accelerators is a critical decision that directly affects both performance and cost. Let's start with CPUs. CPUs are ideal for tasks such as data preprocessing, feature engineering, and lightweight inference. They are cost-effective, widely available, and do not require specialized configurations. For many workloads, especially non-deep learning tasks, CPUs are the most efficient choice. Next, we have GPUs. GPUs are designed for parallel processing and are highly effective for deep learning workloads. Training neural networks or running high-throughput inference is significantly faster on GPUs. However, GPUs are expensive, and using them without proper utilization leads to wasted cost. This is where many teams make mistakes, allocating GPUs when the workload does not justify it. Finally, we have specialized accelerators, such as TPUs or AWS-specific chips like Inferentia and Trainium. These are optimized for specific types of workloads and can offer the best performance per dollar at scale. However, they come with trade-offs, including setup complexity and limited compatibility. From an ML engineering perspective, the key is to align the compute resource with the workload. Always ask, do I really need a GPU for this task? The key takeaway is that choosing the right compute type is one of the simplest yet most powerful ways to optimize cost. Now let's introduce one of the most powerful cost-saving tools in cloud computing: spot instances. As described in your material, spot instances are unused cloud capacity that is offered at a significantly reduced price, sometimes up to 90% cheaper than on-demand instances. This makes them extremely attractive for cost optimization. However, there is a trade-off. Spot instances can be interrupted by the cloud provider when the capacity is needed elsewhere. This means your workload can be stopped at any time. Because of this, spot instances are not suitable for all workloads. They are ideal for batch processing, training jobs, and hyperparameter tuning, tasks that can tolerate interruptions. On the other hand, they should not be used for real-time inference or latency-sensitive systems, where interruptions would impact users. From an ML engineering perspective, spot instances are a strategic tool. When used correctly, they can dramatically reduce training and experimentation costs. The key takeaway is that spot instances provide massive cost savings, but they require careful workload selection. Now let's discuss how to use spot instances safely and effectively. The biggest challenge with spot instances is handling interruptions. As shown in your material, the solution is to design systems that are resilient. The most important technique is checkpointing. This means saving the state of your model periodically during training. If the instance is interrupted, you can resume from the last checkpoint instead of starting over. Another important strategy is monitoring interruption signals. Cloud providers typically notify you before terminating a spot instance, allowing you to take action. Fallback strategies are also critical. If a spot instance becomes unavailable, your system can switch to an on-demand instance to continue the workload. Combining spot and on-demand instances provides both cost savings and reliability. Additionally, spot instances are best used for distributed or batch workloads. These workloads can be split into smaller tasks, making them more resilient to interruptions. As your material highlights, robust checkpointing transforms interruptions from failures into minor pauses. From an ML engineering perspective, this is about designing fault-tolerant systems. The key takeaway is that with the right architecture, spot instances can unlock massive cost savings without compromising reliability. Now let's talk about scaling and how to do it without losing control of costs. As systems grow, one of the biggest risks is runaway cost. This happens when resources scale up but do not scale down efficiently. One of the most effective solutions is auto-scaling endpoints. This allows your system to dynamically adjust capacity based on real-time demand. For example, during peak traffic, the system scales up to handle requests. When traffic drops, it scales down to reduce cost. Another important strategy is choosing between batch and real-time processing. Not all workloads need to run in real time. Many tasks can be deferred and processed in batches, which is significantly cheaper. As highlighted in your material, always-on endpoints can lead to idle capacity, which is essentially wasted money. Eliminating idle resources is critical. Techniques such as scale-to-zero policies ensure that resources are not running when they are not needed. Monitoring utilization is also essential. Without visibility, it is impossible to optimize. From an ML engineering perspective, scaling should always be tied to actual demand, not assumptions. The key takeaway is that smart scaling ensures performance while keeping costs under control. Now let's bring everything together with a cost-aware engineering mindset. As emphasized in your material, cost efficiency should not be treated as an afterthought. It must be built into every stage of the ML lifecycle. Starting with data, you should curate, compress, and cache intelligently. Storing and processing unnecessary data increases both storage and compute costs. During training, use techniques like early stopping, pre-trained models, and spot instances to reduce compute usage. In deployment, scale systems based on demand and use batch processing where possible instead of always-on infrastructure. One of the most important principles is continuous monitoring. Cost optimization is not a one-time task. It requires ongoing measurement and iteration. Another key concept is the feedback loop. By continuously analyzing cost and performance, you can refine your system over time. From an ML engineering perspective, this mindset is what separates good engineers from great ones. Great engineers design systems that are not only functional, but also efficient, scalable, and sustainable. The key takeaway is this: cost efficiency is not about cutting corners. It is about building smarter, more optimized systems from the ground up. Now let's understand the structure of the exam. As shown in your material, the exam typically consists of around 65 questions that must be completed within approximately 130 minutes. This gives you about 2 minutes per question. This immediately highlights the importance of time management. The exam includes a mix of multiple choice and scenario-based questions. These questions are designed to test your understanding of real-world AWS use cases. Another important detail is that no coding is required. This is not a programming test. Instead, it focuses entirely on architecture and decision-making. Every question is framed around a scenario. You are given a business problem or technical requirement, and your job is to choose the best solution. This means you need to be comfortable analyzing situations quickly and identifying the key requirements. Speed, accuracy, and prioritization all matter equally. You cannot spend too much time on any one question, and you must be able to move forward even when unsure. From an ML engineering perspective, this exam evaluates your ability to design systems, not just build models. The key takeaway is that understanding the format helps you manage time effectively and approach each question with the right strategy. Now, let's look at how questions are structured. As your material explains, most questions begin with a business problem. This could be something like reducing cost, improving performance, or scaling a system. Next, technical constraints are introduced. These might include latency requirements, compliance needs, existing infrastructure, or budget limitations. These constraints are extremely important because they guide your decision. Finally, you are asked to choose the most optimal solution. This is where many candidates struggle. Multiple answers may technically work, but only one aligns best with AWS best practices and the constraints provided. For example, if a question emphasizes cost efficiency, then a high-performance but expensive solution is likely incorrect. If a question mentions scalability, then your solution must handle growth effectively. From an exam strategy perspective, you must train yourself to identify keywords such as minimize cost, serverless, or low latency. These keywords are signals that guide your answer. The key takeaway is that every question is a structured scenario. If you understand how to read it correctly, you can significantly increase your accuracy. Now let's discuss the most common traps that candidates fall into. One of the biggest traps is over-engineering. Many candidates choose complex solutions because they seem more impressive. However, AWS strongly favors simplicity and managed services. Another major mistake is ignoring cost. If the question mentions cost optimization, then cost is not optional. It is a requirement. Misreading the question is another critical issue. As highlighted in your material, missing a single keyword such as existing system or serverless can completely change the correct answer. There is also a bias toward complexity. Many candidates assume that more components mean a better solution. In reality, the best solution is often the simplest one that meets all constraints. Another trap is rushing without fully understanding the scenario. While time is limited, careless reading can lead to incorrect answers. From an exam strategy perspective, awareness of these traps is extremely powerful. The key takeaway is this: avoid complexity, pay attention to constraints, and always choose the simplest solution that satisfies the requirements. Now let's talk about one of the most important concepts in the exam: trade-offs. As shown in your material, the exam tests your ability to balance competing priorities, not optimize for just one. For example, the cheapest solution is not always the best. If it fails under load or cannot scale, it is not a valid solution. Similarly, the fastest solution is not always necessary. Real-time systems are more expensive, so they should only be used when explicitly required. This is where architectural thinking comes in. You need to evaluate cost, performance, scalability, and reliability together, not in isolation. Another key concept is scalability. If a question mentions growth or increasing demand, your solution must be able to handle it. Ignoring scalability is a common mistake. From an ML engineering perspective, this is exactly how real-world systems are designed. Every decision involves trade-offs. The diagram in your material emphasizes this idea: balancing cost, performance, and scalability through architectural judgment. The key takeaway is this: the exam is testing your ability to think like an architect, balancing trade-offs and selecting the most practical, scalable, and cost-effective solution. Now let's focus on one of the most important parts of the exam: scenario-based questions. As highlighted in your material, these questions simulate real-world situations. You are given a business problem, along with data, constraints, and sometimes ambiguity. Your task is not just to understand the problem, but to design the best possible solution. This requires system-level thinking. The first step is to identify the goal. What is the organization trying to achieve? Is it reducing cost, improving performance, increasing scalability, or ensuring compliance? Next, you need to parse the constraints. These could include cost limits, latency requirements, existing infrastructure, or security requirements. These constraints are critical because they narrow down your options. Finally, you map the requirements to AWS services. This is where your knowledge of services like S3, SageMaker, Lambda, and Glue comes into play. The challenge is that multiple solutions may work, but only one aligns best with all constraints. From an exam perspective, scenario-based questions test your ability to think like a real-world engineer. The key takeaway is this: always focus on the goal, respect the constraints, and map to the most appropriate AWS solution. Now let's look at a structured approach to solving any scenario-based question. As outlined in your material, the first step is to identify the problem. What exactly is being asked? Next, identify the constraints. These are often hidden in the question and include cost, latency, scalability, or compliance requirements. Once you understand the problem and constraints, you can begin eliminating incorrect options. This is a powerful strategy. In most cases, you can remove at least 2 options immediately because they clearly violate constraints. After narrowing down your choices, you compare the remaining options based on trade-offs. Which one is more cost-effective? Which one scales better? Which one aligns with AWS best practices? Finally, you select the best solution. This step-by-step approach prevents confusion and improves accuracy. Another key benefit is speed. Instead of overthinking, you follow a structured process. From an exam strategy perspective, consistency is key. Apply the same method to every question. The key takeaway is this: a systematic approach allows you to solve complex questions quickly and confidently. Now, let's talk about architecture patterns that frequently appear in the exam. As highlighted in your material, one of the most common patterns is the data ingestion pipeline. This typically involves collecting raw data, storing it in S3, processing it using ETL tools, and preparing it for model training. Another important pattern is the ML lifecycle. This includes training, deployment, and monitoring. You should clearly understand where services like SageMaker fit into each stage. You will also encounter batch versus real-time processing patterns. Batch processing is used for scheduled workloads and is generally more cost-efficient. Real-time processing is used for immediate responses and is often event-driven, using services like Lambda. Understanding when to use each is critical. These patterns appear repeatedly in different forms across exam questions. From an ML engineering perspective, recognizing these patterns allows you to quickly identify the correct solution without analyzing every detail from scratch. The key takeaway is this: learn to recognize common architecture patterns. They will help you answer questions faster and more accurately. Now let's focus on mapping problems to AWS services. As shown in your material, certain AWS services appear repeatedly in exam scenarios. For example, S3 is almost always the default choice for scalable and durable data storage. If the question involves storing large amounts of data, S3 is often the correct answer. Glue is commonly used for ETL pipelines. Whenever you see data transformation or pre-processing, Glue is a strong candidate. SageMaker is the core service for machine learning. It handles training, tuning, and deployment. Lambda is used for lightweight, serverless compute, especially in event-driven architectures. CloudWatch is used for monitoring and observability. The key is not just knowing what these services do, but knowing when to use them. Every question is essentially asking, which service best fits this requirement? From an exam perspective, building a mental map of AWS services is essential. The key takeaway is this: quickly mapping requirements to the right AWS service is one of the most important skills for success in the exam. Now let's bring everything together with a winning exam strategy. As emphasized in your material, the first rule is to read every word carefully. Keywords like minimize cost, existing system, or serverless are not random. They are signals. Missing one keyword can lead to the wrong answer. The second strategy is elimination. remove clearly incorrect options first. This simplifies the decision-making process and increases your chances of selecting the correct answer. Third, manage your time effectively. Do not get stuck on difficult questions. Flag them and move on, then return later if needed. Another important strategy is practice. As your material highlights, repeated exposure to scenario-based questions builds pattern recognition. Over time, questions that initially take 2 minutes can be solved in under a minute. Finally, stay calm and think logically. This exam is not designed to trick you. It is designed to test your ability to make sound decisions. From an ML engineering perspective, this is exactly how real-world problem-solving works. The key takeaway is this: success comes from careful reading, structured thinking, and consistent practice. Now let's bring everything together and look at the complete system architecture you've built in this capstone project. At a high level, this architecture represents a full end-to-end machine learning system running on AWS. It starts with data ingestion and flows all the way to deployment, monitoring, and continuous improvement. The pipeline begins with raw data stored in Amazon S3. As you've seen throughout the course, S3 serves as the foundation for scalable and durable data storage. It acts as the central data lake for all incoming data. From there, data is processed using ETL pipelines, typically powered by AWS Glue. This step cleans, transforms, and prepares the data for downstream tasks. Once processed, features are generated and optionally stored in a feature store for reuse and consistency across training and inference. Next comes the model training stage using Amazon SageMaker. Here, the model is trained, validated, and tuned. SageMaker manages the training infrastructure, making it scalable and efficient. After training, the model is deployed to a real-time endpoint or configured for batch inference, depending on the use case. This allows the system to generate predictions either instantly or in scheduled batches. Monitoring is handled using services like CloudWatch, which track model performance, system health, and operational metrics. This is critical for detecting issues such as model drift or performance degradation. As highlighted throughout your learning, this system also includes feedback loops. Predictions and outcomes are fed back into the system to improve future models through retraining. If you think about it, this architecture reflects many of the patterns we discussed earlier: data pipelines, ML lifecycle, and scalable deployment systems. From an ML engineering perspective, this is not just a model. It is a production-ready system. The key takeaway is this: you now understand how to design and build an end-to-end ML architecture that is scalable, efficient, and aligned with real-world industry practices.